Welcome to the Whispering Scientist, where the vast mysteries of the cosmos meet the gentle quiet of evening contemplation. Tonight, as you settle into the soft embrace of twilight and let the day's concerns drift away like distant stars, we begin an extraordinary journey into one of the universe's most profound and beautiful secrets. I am delighted you've chosen to spend these precious moments of transition with us, exploring the hidden architecture that holds everything we know in its invisible embrace. As you find your most comfortable position and allow your breathing to slow into the natural rhythm of rest, imagine yourself floating peacefully in the serene darkness of space, surrounded by the gentle glow of distant galaxies. Tonight marks the beginning of our exploration into dark matter, that enigmatic presence that makes up most of our universe yet remains completely invisible to our eyes and instruments. It is the cosmic secret whispered across billions of years, the hidden thread that weaves through the vast tapestry of existence. Before we embark on this gentle voyage through the unseen realms of space, I'm genuinely curious to know where in the world you're listening from tonight. There's something wonderfully comforting about knowing that curiosity about the cosmos connects us across continents, time zones, and cultures. Whether you're nestled in a cozy bedroom in Tokyo, relaxing in a quiet apartment in London, or unwinding on a peaceful evening in New York, we're all united under the same star-filled sky, pondering the same magnificent mysteries. If you're new to The Whispering Scientist, welcome to our tranquil corner of scientific exploration. Please consider giving this video a gentle like and subscribing to join our growing community of cosmic wanderers who seek both knowledge and peace in equal measure. Your support helps these quiet journeys through science and the universe reach others who might find solace in contemplating the grand mysteries of existence. To those cherished listeners who are already part of our sleepy community of stargazers, thank you sincerely for your continued presence and curiosity. Don't forget to tap the notification bell, ensuring you'll never miss our next peaceful expedition through the cosmos. My sincere hope is that tonight's exploration isn't so captivating that it prevents your well-deserved rest, but if it does keep you awake a little longer, at least you'll drift off to sleep carrying a deeper appreciation for the universe's most profound secrets. Sometimes the most beautiful discoveries come not from what we can see, but from understanding what remains hidden in the spaces between the light. The universe we observe, with all its glittering galaxies, shimmering nebulae and brilliant stars, represents merely the surface of something far grander and more mysterious than we ever imagined. What exactly holds these cosmic structures together when there isn't enough visible matter to accomplish such a monumental task? The answer lies in dark matter, a phrase that might initially sound like something from science fiction, but represents one of the most patient and fundamental aspects of our cosmos. Dark matter doesn't announce its presence with the dramatic flare of exploding supernovas or the brilliant light of stellar birth. Instead, it operates with quiet dignity, never glowing with stellar fire, never colliding with the spectacular violence of cosmic catastrophes. Yet its invisible weight methodically sculpts the universe into the magnificent, intricate structure we observe through our most powerful telescopes tonight. For nearly a century, astronomers have been gathering subtle clues, observing phenomena that simply defy explanation by visible matter alone. Galaxies spin with seemingly impossible speeds, their outer stars racing around their centers far too quickly to remain gravitationally bound. Stars remain steadfastly organized in their cosmic neighborhoods when basic physics suggests they should scatter like leaves in an autumn windstorm. Entire clusters containing thousands of galaxies move through space as if guided by invisible hands, maintaining their cohesive formations across billions of years of cosmic evolution. Each anomaly, each deviation from our expectations based on visible matter, has consistently pointed toward the same astonishing conclusion. There exists far more to the universe than meets even our most sensitive instruments. Our journey together over the coming chapters will carefully trace these whispers of evidence, from the very first strange observations that hinted at a deeper reality, to the immense invisible filaments that stretch between galactic superclusters. Like the universe's own nervous system, will follow the subtle evidence written in the gentle bending of starlight as it passes through regions of space that appear empty but clearly contain enormous masses. We'll explore the faint afterglow of the Big Bang itself, discovering how it carries encoded messages about the invisible scaffolding that shaped the early universe. Along our path, we'll encounter the tiny, hypothetical particles that might constitute this hidden cosmic mass and delve into the ingenious, patient experiments tucked deep underground in abandoned mines, quietly listening for the faintest touch of these elusive visitors from the dark. There will be no intimidating equations to decipher tonight, no dense scientific jargon to untangle or memorize. Instead, we'll immerse ourselves completely in the slow, steady rhythm of discovery, following a mystery that has profoundly shaped everything we know and observe in the cosmos. As you relax and allow your mind to wander freely among the stars, picture the universe as an immense, intricate tapestry stretching across billions of light years. The stars, the colorful nebulae, the spiral galaxies that grace our deepest space photographs, these represent the exquisite embroidery, the glittering surface details that catch our attention and inspire our wonder. But the true, foundational fabric of this cosmic tapestry, the vast and silent weave that supports and structures all the luminous beauty we admire, consists entirely of the dark matter that fills the space between and around every visible object. Tonight, we begin our gentle descent into understanding this invisible foundation that makes all cosmic architecture possible. Hold that image of the cosmic tapestry gently in your mind as we drift backward through time to a quieter era of astronomy, when glass photographic plates captured starlight with patient precision and mountaintop observatories creaked softly in the cold night air. In the peaceful decades between the two world wars, when scientific discovery moved at the thoughtful pace of handwritten calculations and telescopes required human guidance to track the stars, a brilliant Swiss astronomer named Fritz Zwicky was about to stumble upon one of the universe's most profound secrets, working in the clear mountain air of California's Mount Wilson Observatory. During the early 1930s, Zwicky turned his attention away from individual stars towards something far grander and more mysterious. His target was a distant congregation of galaxies called the Coma Cluster, a vast celestial city containing thousands of island universes, each one a complete galaxy filled with billions of stars, all drifting together through the immense emptiness of intergalactic space like luminous lanterns floating on an invisible sea. Zwicky approached this cosmic assembly with the methodical precision that characterized the finest astronomical work of his era, but what he discovered would challenge everything astronomers thought they understood about the universe's composition. As he carefully measured how fast individual galaxies were moving within the cluster, tracking their velocities through subtle shifts in the wavelengths of their light, the numbers began telling a story that defied all conventional wisdom about gravity's behavior on such enormous scales. The galaxies were racing around the cluster's center at speeds that seemed absolutely impossible according to Newton's well-tested laws of gravitation. Based on all the visible matter Zwicky could observe through his telescope, every glowing star, every luminous gas cloud, every detectable wisp of cosmic dust, there simply wasn't enough gravitational pull to keep such rapidly moving objects bound together in a stable formation. The mathematics were unforgiving in their clarity. These galaxies should have scattered into the cosmic void eons ago, flying apart like sparks from a dying campfire. Yet there they remained, serenely orbiting within the cluster's gravitational embrace, their movements suggesting the presence of something far more massive than anything visible through even the most powerful telescopes of the time. Zwicky's calculations were based on what physicists call the virial theorem, an elegant principle that connects the observed motions of objects within a gravitational system to the total mass that system must contain. Think of children on a carousel. Gentle turns require only a light grip, but faster spins demand someone holding on much more tightly. In the Coma cluster, the galaxies were spinning fast with seemingly too little visible mass to provide the necessary gravitational grip. When Zwicky applied this fundamental principle to his observations, the results were nothing short of astounding. The cluster appeared to weigh hundreds of times more than what could be accounted for by all its visible components combined. It was as if he had discovered a massive, invisible elephant in the cosmic living room, something so enormous that it dominated the entire gravitational landscape, yet remained completely hidden from direct observation. With his characteristic directness and impatience with unnecessary complexity, Zwicky coined a straightforward term for this missing gravitational ingredient: dunkle materie, or dark matter. He wasn't attempting to be poetic or mysterious. He simply needed a practical name for whatever invisible substance was clearly present, but stubbornly refusing to reveal itself through any known form of light or radiation. The phrase was pure scientific bookkeeping and accounting entry for mass that the equations demanded, but the telescopes couldn't find. The scientific community's initial reaction to Zwicky's extraordinary claims was, perhaps understandably, one of skepticism bordering on dismissal. This lukewarm reception wasn't helped by Zwicky's notorious personality. He had earned a formidable reputation throughout his career as a brilliant but extraordinarily difficult colleague, someone whose sharp tongue and impatient brilliance often alienated his peers. He once famously described some of his fellow astronomers as spherical bastards, explaining with characteristic bluntness that they were bastards no matter which direction you approached them from. While his intellectual capabilities were never questioned, his diplomatic skills left considerable room for improvement. This unfortunate combination of revolutionary scientific claims and abrasive personality meant that many astronomers found it easier to question Zwicky's methodology than to seriously consider the possibility that the universe might be fundamentally different from their comfortable assumptions. The prevailing cosmological picture of the 1930s portrayed the cosmos as consisting primarily of familiar visible matter: stars, planets, gas clouds, and dust particles. The radical notion that most of the universe's substance might be completely invisible seemed not just unlikely, but almost philosophically offensive to many. Scientists of the era, perhaps Zwicky, had made systematic errors in his velocity measurements, colleagues suggested. Maybe the light from these distant galaxies was being distorted by unknown effects during its long journey through intergalactic space. It seemed far more reasonable and intellectually comfortable to assume that the problem lay in the observational data rather than in humanity's fundamental understanding of cosmic architecture. Yet, Zwicky's mathematics remained stubbornly consistent, and his observational techniques proved sound under scrutiny. Even when other astronomers repeated his measurements using different instruments and methods, the same impossible pattern emerged. The galaxies in the Coma cluster were indeed moving too quickly for their visible matter to explain, and no amount of careful reanalysis could make this inconvenient fact disappear. To truly appreciate what Zwicky had discovered, imagine floating in the darkness of intergalactic space, looking down upon the Coma cluster from a vast distance. Thousands of galaxies would gleam before you like scattered lanterns drifting across a dark ocean, each one a magnificent collection of billions of stars. Between these galactic lanterns lies what appears to be nothing but empty blackness, vast regions of space that seem completely devoid of matter. But that apparent emptiness, Zwicky realized, was actually heavy with something completely invisible, an unseen web of gravitational influence that bound each luminous galaxy firmly in place. If you could somehow strip away this hidden mass, the galaxies would immediately begin scattering like sparks from a dying fire, their organized cluster dissolving into chaos as each galaxy followed its own independent path through the expanding universe. Zwicky's discovery represented far more than just an interesting anomaly in one particular cluster of galaxies. He had planted the first seed of doubt in humanity's neat, luminous picture of the cosmos, forcing scientists to confront the possibility that everything they could observe directly might represent only the thinnest surface layer of something far grander and more mysterious. He couldn't have known it at the time, but his lonely calculations were creating the first cracks in the universe's bright facade, revealing hints of a hidden architecture that had been waiting patiently to be discovered. What Zwicky had stumbled upon wasn't simply a measurement error or a gap in astronomical data. It was a truth so profound that it would eventually transform cosmology itself, revealing that the visible universe was not the whole story. The luminous galaxies filling the night sky were merely decorations on a far grander, invisible structure. His whisper from the coma cluster would grow into a steady voice that could no longer be ignored, marking the beginning of humanity's recognition that we live in a universe where darkness shapes the light. Zwicky's whisper from the coma cluster lingered in the scientific literature like a half-remembered melody, waiting patiently for someone to recognize its harmony and give it voice. Decades passed in this quiet suspension, with his dunkel materia remaining largely dismissed as the eccentric pronouncement of a brilliant but difficult personality. Yet the cosmos, in its infinite patience, continued to hold its secret, waiting for another observer with the dedication to truly listen to what the universe was trying to say. As the middle of the 20th century arrived, astronomy was undergoing a gentle revolution. New telescopes pierced deeper into space with unprecedented clarity, and more sensitive instruments could detect the subtlest whispers of light from distant cosmic shores. Among the astronomers leading this transformation was Vera Rubin, a calm, methodical scientist whose approach to discovery embodied the very essence of patient scientific inquiry. She didn't seek fame or dramatic theoretical breakthroughs. Instead, she found profound satisfaction in the quiet rhythm of careful observation, trusting that the universe would reveal its truths to those willing to listen with genuine attention. Rubin's fascination centered on spiral galaxies, those magnificent cosmic pinwheels that grace our deepest space photographs with their elegant, sweeping arms. From our distant vantage point, these galactic systems appear to rotate with the unhurried grace of slowly spinning records, their luminous spiral patterns suggesting perfect harmony and mathematical beauty. But beneath their serene appearance lay a puzzle that would fundamentally challenge everything astronomers thought they understood about how gravity organizes matter on the grandest scales imaginable. The expected behavior of rotating galaxies follows principles that feel both intuitive and mathematically elegant. When any system is held together primarily by gravitational attraction, objects closer to the center should naturally orbit faster than those farther away, simply because they experience stronger gravitational pull from the concentrated mass at the core. This fundamental relationship governs cosmic motion from the smallest scales to the largest, representing one of the most reliable and predictable patterns in all of physics. Our own solar system demonstrates this principle with beautiful clarity. Mercury, nestled in the Sun's intense gravitational embrace, races around its orbit in just 88 Earth days, while Neptune, drifting in the cold outer reaches nearly 30 times farther from our star, requires over 160 years to complete a single leisurely circuit. The rule is as comforting as it is precise. The farther you are from the central mass, the weaker the gravitational pull becomes, and consequently, the slower your orbital motion should be. When Rubin and her collaborator, Kent Ford, began their meticulous measurements of stellar velocities within spiral galaxies, they naturally expected to find this same elegant pattern reproduced on cosmic scales, using sophisticated spectrographs that could detect the subtle Doppler shifts in starlight, those minute changes in wavelength that occur when objects move toward or away from us. They began systematically mapping the speeds of stars at varying distances from galactic centers. The technique itself was elegantly straightforward in concept, though demanding extraordinary precision in execution. Just as the pitch of a train whistle shifts higher as it approaches and lower as it recedes, the light from stars shows similar shifts that reveal their motion relative to Earth. By measuring these tiny spectral changes with remarkable accuracy, Rubin and Ford could trace the velocities of stars throughout entire galaxies, creating what astronomers call rotation curves, graphs plotting stellar velocity against distance from the galactic center. What emerged from their painstaking observations was both stunningly consistent and completely revolutionary. Instead of the gentle downward slope that theory predicted, with outer stars moving progressively slower than their inner counterparts, the rotation curves remained stubbornly, impossibly flat. Stars on the distant outskirts of galaxies were moving just as rapidly as those near the center, as if the entire galactic disk was rotating like a rigid wheel, rather than following the fluid dynamics that gravity should naturally impose. To visualize this extraordinary discovery, imagine a record player spinning in a darkened room where only the center portion is illuminated. You can see the inner part of the record rotating at normal speed, but somehow the outer edge, invisible in the darkness, is also spinning at exactly the same rate, defying every expectation based on mechanical physics. The music, in this cosmic analogy representing gravitational force, must be playing evenly across the entire disk, sustained by something far beyond the visible mechanism at the center. Galaxy after galaxy revealed this same impossible pattern with monotonous consistency. The outer regions, which should have been moving slowly enough that centrifugal force couldn't overcome the weak gravitational pull from the distant galactic core, were instead racing around their orbits at speeds that defied all conventional understanding. According to every calculation based on visible matter alone, these outer stars should have been flung into intergalactic space billions of years ago, scattered like droplets from a spinning wheel. Yet there they remained, serenely following their rapid orbits in perfect stability, held in place by some invisible gravitational influence that reached far beyond the luminous boundaries of their galaxies. The implications were staggering. Something unseen had to be providing enormous additional gravitational pull, not just a small correction to the equations, but several times more mass than all the visible stars, gas, and dust combined could account for. Rubin described her findings with characteristic scientific restraint, but behind the careful language of her research papers lay something truly astonishing. These galaxies were being embraced by vast halos of invisible matter that extended far beyond their bright spiral arms, reaching into the apparent emptiness of space like ghostly hands holding each stellar system in perfect gravitational balance. Whatever this unseen material was, it wasn't emitting light, wasn't absorbing radiation, and wasn't hiding behind obscuring clouds of dust. It was simply there, invisible but undeniable, forming enormous cocoons around every galaxy she studied. As Rubin expanded her survey to include systems of every size and type, from tiny dwarf galaxies to enormous spiral giants, the same pattern emerged with remarkable regularity. Flat rotation curves weren't an anomaly or measurement error. They represented a fundamental rule of galactic architecture. What had begun as Zwicky's lonely voice from a single cluster had become a universal chorus, with every galaxy singing the same quiet song of hidden mass. The initial skepticism from the astronomical community echoed the doubts that had greeted Zwicky's observations decades earlier. Perhaps there were systematic errors in the velocity measurements, colleagues suggested, or maybe the galaxies themselves were behaving according to some unknown physical principle that mimicked the effects of missing mass without actually requiring invisible matter. But Rubin's methodology was thorough beyond question. She repeated her measurements using different instruments, refined her techniques to eliminate every possible source of error, and expanded her sample size until the evidence became absolutely unassailable. The galaxies weren't misbehaving according to some exotic physics. They were simply revealing the universe's hidden architecture with crystal clarity, whispering truths that had been waiting patiently for someone to notice. What made Rubin's work particularly remarkable wasn't just the precision of her science, but the quiet grace with which she approached these revolutionary discoveries. She didn't present her findings as cosmic upheavals that would overturn established physics. Instead, she treated them as natural steps in humanity's ongoing conversation with the universe, another layer of truth that had been waiting for the right moment and the right observer to bring it into the light. Her discovery transformed dark matter from Zwicky's controversial hypothesis into an essential component of cosmic architecture. If every galaxy required an invisible halo to maintain its elegant structure, then this mysterious substance had to be everywhere, woven throughout the cosmos like an invisible web supporting all the luminous beauty we observe. The bright stars and glowing nebulae that capture our imagination were merely the glittering surface of something far grander and more mysterious, a universe where darkness provides the foundation for all the light we see, with Rubin's flat rotation curves now resonating through the astronomical community like a quiet but persistent melody. The evidence for dark matter was evolving from curious anomaly into something far more substantial and undeniable. Yet even as galaxies revealed their hidden halos through the graceful motions of their stars, scientists yearned for additional confirmation, some independent line of evidence that could corroborate what these velocity measurements were whispering. The universe, with its characteristic patience toward careful observers, was about to provide exactly that confirmation through one of nature's most elegant and incorruptible witnesses, gravity itself. Gravity, as it turns out, is perhaps the most reliable gossip in the entire cosmos, utterly incapable of keeping secrets or telling lies. No matter how invisible, elusive, or shy something might be, if it possesses mass, gravity will inevitably betray its presence through unmistakable effects that ripple across the fabric of space-time itself. You can hide from the most sensitive telescopes, refuse to emit or absorb any form of radiation, slip through ordinary matter as if it doesn't exist, but you cannot hide from gravity's honest testimony about your presence in the universe. This fundamental truth traces back to Einstein's revolutionary insight into gravity's true nature. Rather than imagining gravity as some mysterious force reaching across empty space to tug on distant objects, Einstein revealed that massive objects actually warp the very fabric of space-time around them. Picture pressing a heavy bowling ball into the center of a stretched rubber sheet. The depression it creates changes the geometry of the entire surface, causing marbles rolled across that sheet to follow curved paths as they encounter the warped terrain. In precisely this elegant way, every object with mass, from the smallest asteroid to the most massive galaxy cluster, presses gently into the cosmic fabric, creating subtle indentations that alter the paths of everything passing nearby. The more massive an object, the deeper its gravitational imprint becomes, and the more dramatically it influences the motion of matter and energy traveling through its cosmic neighborhood. This warping of space-time has a particularly profound effect on light, those streams of photons that ordinarily travel in perfectly straight lines across the universe. When light encounters regions where massive objects have curved the fabric of space, it has no choice but to follow those curves, bending and twisting along paths that would seem impossible if we considered only the apparently empty vacuum through which it appears to travel. The light doesn't bend because it wants to, but because the stage itself, the very geometry of space-time, has been reshaped by the presence of mass. This phenomenon, known as gravitational lensing, provides astronomers with one of their most powerful and visually striking tools for detecting invisible matter throughout the cosmos. Even though dark matter stubbornly refuses to shine or reflect light directly, its gravitational influence still warps the paths of photons traveling from distant galaxies positioned behind it. It's rather like watching ripples spread across a perfectly still pond and, from their intricate patterns alone, discerning the size and movement of some unseen creature swimming beneath the opaque surface. The effect can be dramatically obvious when the gravitational lens is particularly massive, such as an enormous galaxy cluster containing thousands of individual galaxies. In these spectacular cases, light from objects far behind the cluster can be stretched into long, graceful arcs or even complete rings of brilliance known as Einstein rings, named in honor of the physicist who first predicted such exotic optical phenomena. These cosmic mirages allow astronomers to peer deeper into space than would otherwise be possible, using the cluster's gravity as a natural telescope that magnifies and brightens distant objects normally too faint to observe. More importantly, for unraveling the dark matter mystery, these lensing effects provide a completely independent method for measuring the total mass of galaxy clusters, regardless of whether that mass happens to emit light or remain stubbornly invisible. By analyzing the precise shapes and positions of lensed background galaxies, astronomers can create detailed maps showing exactly where mass concentrates within the lensing cluster, including any dark matter that might be lurking there unseen, even when the lensing effects are subtle, manifesting as only gentle stretching or shearing of countless background galaxies. These minute distortions accumulate into significant measurable patterns. Astronomers can detect this weak lensing across vast regions of sky, creating statistical maps that reveal the gravitational landscape of the cosmos and, by extension, the distribution of dark matter itself. It represents delicate science demanding immense precision, but the reward proves unparalleled, a direct map of the universe's true mass distribution. Perhaps the most compelling and dramatic piece of lensing evidence emerged from observations of a system called the Bullet Cluster, where two massive galaxy clusters had collided approximately 150 million years ago. When astronomers studied this cosmic aftermath using both visible light and gravitational lensing techniques, they discovered something profoundly revealing about dark matter's fundamental nature. The hot gas that makes up most of the visible matter in galaxy clusters had behaved exactly as expected during the collision. The two gas clouds crashed together, slowed down through electromagnetic interactions, and settled into a bright region glowing intensely in X-ray wavelengths. This luminous debris clearly marked where the visible matter had come to rest after the violent encounter, like cosmic wreckage scattered across space, but gravitational lensing maps told a completely different story. The bulk of each cluster's mass, as revealed by its effects on background light, had passed straight through the collision largely unaffected. The invisible mass had glided past itself like two ghostly formations, each maintaining its original trajectory, while the visible matter lagged behind in the collision zone. This separation between luminous gas and gravitational influence was absolutely stunning, direct evidence that most of each cluster's mass consisted of something that could pass through cosmic collisions without slowing down, heating up, or interacting in any detectable way. The Bullet Cluster became a kind of cosmic smoking gun for dark matter, a natural experiment conducted on scales so vast that no earthly laboratory could hope to replicate it. The collision had effectively separated the visible and invisible components of these galaxy clusters, allowing astronomers to study each component independently and confirm that they behaved according to completely different physical rules, this gravitational testimony extended far beyond individual dramatic collisions. As lensing surveys mapped ever larger volumes of space, they revealed the same invisible scaffolding that galaxy rotation curves had suggested, vast halos of unseen matter surrounding every galaxy, connected by long filaments stretching across the cosmic web like an intricate network of gravitational highways. The beauty of gravitational lensing as a dark matter probe lies in its fundamental honesty. Light cannot lie about the paths it follows through curved space-time, and mass cannot hide its gravitational influence, no matter how invisible it might be, to other forms of observation. Every bend in a light ray, every stretched galaxy image, every subtle distortion carries reliable information about the distribution of matter, both seen and unseen along our line of sight. Through this cosmic testimony of bent light, astronomers had found their independent confirmation of dark matter's existence. The same invisible halos that Rubin's rotation curves demanded were now being mapped directly through their gravitational effects on light from the distant universe. The evidence was no longer circumstantial. It was written across the sky in the elegant language of curved space-time, spelled out in graceful arcs and rings where gravity had transformed distant galaxies into luminous calligraphy. As these gravitational maps grew more detailed and comprehensive, they began revealing something even grander, the true architecture of the universe itself, a vast network of dark matter scaffolding that supported and shaped all the luminous structures we could observe directly. The stage was now perfectly set for exploring this invisible framework on the grandest scales imaginable, tracing the cosmic web through patient testimony of light, bent by unseen hands reaching across billions of years, those graceful arcs and rings of bent starlight, gravity's honest testimony written across the cosmic canvas, had revealed far more than just individual halos surrounding galaxies and clusters. As gravitational lensing maps accumulated across decades of patient observation, they began painting a picture of something grander and more magnificent than anyone had dared imagine. What started as isolated discoveries of dark matter around single cosmic objects gradually revealed itself to be part of an overarching structure that would fundamentally transform our understanding of the universe's deepest architecture. When astronomers first began systematically mapping the three-dimensional positions of millions of galaxies scattered across billions of light-years, they approached the task with reasonable expectations based on their understanding of cosmic evolution. Most assumed they would find galaxies distributed somewhat randomly throughout space, perhaps clustering together here and there due to local gravitational influences, but generally spread out like grains of sand scattered across an infinite beach. The universe, they imagined, would reveal itself as a vast, relatively uniform expanse punctuated by occasional concentrations of matter. Instead, what emerged from these ambitious surveys was something that resembled a living organism more than a random distribution, an immense, interconnected network stretching across cosmic distances that challenged human comprehension. This grand structure became known as the cosmic web, and it represents quite literally the skeleton upon which all visible matter in the universe hangs like delicate ornaments on an invisible Christmas tree. Picture, if you will, the most intricate spider's web you've ever seen, but scaled up to encompass the entire observable universe. Luminous galaxies and brilliant galaxy clusters trace these invisible filaments like strings of pearls draped along unseen supports, while between them lie immense voids, vast regions of space so empty that they contain fewer galaxies than you could count on your fingers, despite spanning hundreds of millions of light-years in every direction. It's as if the universe had organized itself into the most sophisticated architectural framework imaginable, with every galaxy positioned precisely where invisible scaffolding could best support its cosmic weight. The formation of this magnificent structure traces back to the universe's earliest moments, when it existed as an almost perfectly uniform soup of matter and energy, marked only by the tiniest fluctuations in density, variations so subtle they amounted to just 1 part in 100,000. These microscopic ripples in the primordial cosmos were like seeds containing the blueprint for everything that would eventually emerge, every galaxy, every cluster, every vast void that punctuates the cosmic landscape we observe today. Dark matter played the crucial role of patient architect in transforming these gentle ripples into the grand structures we observe today. While ordinary matter, the atoms that would eventually form stars, planets, and living beings, remained too hot and energetic to settle down in the early universe, constantly scattered by intense radiation like leaves in a cosmic windstorm. Dark matter operated with cool indifference to all that electromagnetic chaos. It simply responded to gravity's gentle pull, slowly gathering in regions where those primordial density fluctuations had created slightly more mass than average. Over hundreds of millions of years, these modest concentrations of dark matter grew steadily under their own gravitational attraction, drawing in more material from their surroundings and gradually forming the vast filamentary network that would become the cosmic web's invisible foundation. Only after this dark scaffolding had established itself could ordinary matter begin flowing into the gravitational channels like water finding its way into the grooves of a riverbed, pooling and cooling until conditions became right for the first stars to ignite their nuclear fires. The resulting balance between structure and emptiness creates one of the universe's most striking features. While the cosmic web's filaments are dense with galaxies and dark matter, the voids between them are almost perfectly empty, containing virtually no matter at all. These cosmic deserts are so barren that if our Milky Way galaxy were placed in the center of one, we might never encounter another galaxy within the observable horizon. Yet rather than representing failures or flaws in cosmic architecture, these voids serve essential functions, providing the empty spaces that allow dense regions to exist. Just as silence gives shape to music, modern computer simulations can reproduce this cosmic web with stunning accuracy, starting from the same simple ingredients that shape the real universe: the expansion of space, the pull of gravity, and the presence of dark matter particles that interact only through gravitational force. In these digital universes, scientists watch billions of dark matter particles attract each other over cosmic time, forming networks of structure that match telescope observations with remarkable precision. The fact that such simple initial conditions can produce the complex, beautiful patterns we observe serves as powerful confirmation that we truly understand the invisible forces shaping our cosmos. These simulations reveal the cosmic web as a living, evolving entity. Galaxies continue falling along the filaments like beads sliding down cosmic strings, merging and growing more massive as they encounter one another. The voids gradually expand as the universe's overall expansion stretches the web's structure, making the filaments longer and thinner with each passing billion years. Yet the basic pattern persists, demonstrating the fundamental stability of this dark matter architecture that has endured for most of cosmic history. What makes the cosmic web particularly fascinating is how it influences the galaxies embedded within it. Astronomical observations have revealed that galaxies tend to align themselves along these invisible filaments, their shapes and orientations influenced by the flow of matter through the network. It's as though the entire universe participates in a subtle choreography, with every galaxy moving to rhythms established by the gravitational symphony that began playing shortly after the Big Bang. The web's filaments also serve as cosmic highways, channeling gas and smaller galaxies toward the massive clusters that form at intersection points where multiple strands converge. These nodes represent the universe's most dynamic regions, where ongoing mergers and interactions continue shaping galactic evolution. Meanwhile, galaxies unfortunate enough to find themselves in the vast voids between filaments evolve in relative isolation, their development proceeding at a more leisurely pace without the constant gravitational perturbations experienced by their web-dwelling cousins, as surveys map ever larger volumes of space with increasing precision. The cosmic web reveals itself as both delicate and robust, intricate yet simple in its underlying physics. Each new observation adds detail to our understanding of this invisible framework, showing how dark matter's patient gravitational influence has shaped not just individual galaxies, but the entire cosmic landscape in which we find ourselves embedded. The realization that we live within this vast web of invisible matter transforms our perspective on cosmic architecture. Every galaxy we observe exists precisely where it does because of this underlying dark structure. The luminous universe represents merely the foam on top of an ocean whose depths remain largely hidden, yet whose currents determine where every visible structure finds its place in the grand cosmic symphony. Standing at this threshold of understanding, with the cosmic web's architecture mapped in ever greater detail, we find ourselves naturally drawn to examine the ancient light that still carries messages from when this invisible framework first began taking shape in the universe's earliest moments. The cosmic web's magnificent architecture, with its delicate filaments stretching across billions of light-years and vast voids punctuating the cosmic landscape, reveals the universe's present-day structure in all its invisible grandeur. Yet to truly understand how dark matter orchestrated this grand design, we must journey backward through time to witness the universe's own baby pictures, ancient light that has been traveling toward us for nearly 14 billion years, carrying encoded messages about the invisible scaffolding that guided cosmic evolution from its very beginning. Long before there were stars to illuminate the darkness, before galaxies had gathered into their elegant spiral forms, before planets had condensed from cosmic dust, the entire universe existed as a hot, dense fog of particles and radiation all tangled together in an intimate cosmic dance. Picture the most crowded ballroom imaginable, where photons, those fundamental particles of light, found themselves constantly colliding with free electrons and protons in an endless, restless ballet of energy and matter. The universe wasn't dark during this primordial era. It was blindingly bright, but that brilliance was trapped, unable to travel more than microscopic distances before being absorbed and re-emitted by the dense plasma that filled all of space. In this ancient fog, light and matter were so thoroughly mixed that transparency was impossible. If you could have existed in that cosmic furnace, you wouldn't have seen anything at all, not because there was no light, but because light itself was imprisoned in the swirling chaos of the early universe. Every photon that tried to escape was immediately captured and scattered by the free-floating particles, creating a realm where illumination existed everywhere, but visibility existed nowhere. But as the universe expanded during its first few 100,000 years, it also cooled steadily and inexorably, following the fundamental laws of thermodynamics. When temperatures finally dropped sufficiently, about 3,000 degrees above absolute zero, roughly 380,000 years after the Big Bang, something magical happened that would forever change the nature of cosmic illumination. The free electrons, finally moving slowly enough, were captured by protons, forming the first stable, neutral hydrogen atoms. With electrons now bound within atoms rather than floating freely through space, photons were suddenly liberated from their electromagnetic prison. For the first time since the Big Bang itself, light could travel unobstructed across space, racing outward in all directions like ripples spreading from a stone dropped into an infinite, perfectly still pond. That ancient light has been traveling ever since, stretched and faded by the universe's continued expansion until today it reaches us as a faint, nearly uniform glow permeating every corner of the cosmos. This is the cosmic microwave background radiation, the oldest light in existence, a gentle whisper from the universe's infancy that surrounds us completely. This ancient afterglow flows through every room, every building, every cubic inch of space around Earth. If you tune an old television between channels and observe the static that appears on screen, a tiny fraction of that visual noise consists of photons that began their journey when the universe was less than 400,000 years old, carrying messages from a time before the first star was born. To casual observation, this cosmic microwave background appears perfectly smooth and uniform, like gentle, even warmth radiating from all directions. But when astronomers began studying it with exquisite precision using sophisticated satellites, they discovered something extraordinary hidden within that apparent uniformity. Scattered across this ancient light like delicate freckles were tiny variations in temperature, fluctuations so subtle they amounted to mere thousandths of a degree. Yet these microscopic differences contained the seeds of everything we see in the universe today. These gentle ripples in the ancient light were not random noise or measurement errors. They were the gravitational fingerprints of dark matter already at work in the early universe, shaping the cosmic landscape long before ordinary matter could participate in structure formation. The slightly warmer spots corresponded to regions where matter had begun concentrating under gravity's patient influence, while the cooler areas marked regions that were slightly less dense than average. Over billions of years of cosmic evolution, those warmer spots would grow into the galaxies, clusters and filaments of the cosmic web, while the cooler regions would become the vast voids that separate them. But here lies the remarkable and crucial part of this cosmic story. Without dark matter's early participation, those tiny ripples could never have grown large enough or quickly enough to form the structures we observe today. Ordinary matter, composed of atoms that interact strongly with light and radiation, was still tightly coupled to the cosmic microwave background during this era, buffeted around like dust motes in brilliant sunlight. Every time gravitational attraction tried to pull atoms together into denser concentrations, radiation pressure would push them back apart, preventing any significant structure from forming. Dark matter, however, remained aloof from all this electromagnetic chaos. Since it doesn't interact with light or radiation, it wasn't affected by the intense energy that kept ordinary matter stirred up and unable to settle. While atoms were being tossed about by cosmic forces, dark matter was already pooling quietly under gravity's influence, forming the invisible wells that would later capture ordinary matter once the universe cooled sufficiently for atoms to decouple from radiation. In a very real sense, dark matter gave the universe its crucial head start in structure formation. Those first faint temperature variations in the cosmic microwave background weren't just random fluctuations, they were the shadows cast by dark matter, concentrations that had already begun shaping the cosmos, while ordinary matter was still trapped in its luminous prison. Successive generations of satellites have painted increasingly detailed portraits of this ancient light, creating maps that resemble mottled spheres of subtle color variations. The Cosmic Background Explorer first revealed the faint temperature differences. The Wilkinson Microwave Anisotropy Probe traced their patterns with crisp clarity, and the Planck spacecraft delivered a portrait so detailed that the early universe could be weighed and measured with extraordinary precision. The red regions in these maps indicate areas where the radiation is slightly warmer, while blue areas mark cooler zones, and though these variations might appear random to untrained eyes, they actually reveal the universe's precise recipe with mathematical exactitude. From the specific pattern of these temperature fluctuations, scientists can calculate exactly what the universe is made of: approximately 5% ordinary atomic matter, 27% dark matter, and 68% dark energy, that mysterious force driving cosmic expansion to accelerate. These aren't rough estimates or educated guesses. Their measurements derive directly from the cosmic microwave background's subtle patterns, written into the ancient light like an accounting ledger, carved from photons. The spacing between peaks and valleys in these temperature variations tells us how fast sound waves traveled through the early cosmic plasma, which in turn depends on the precise balance of matter, radiation, and energy that filled the universe during its infancy. It's remarkably similar to listening to the echo of a bell and inferring the bell's size and composition from the sound's characteristics. Except in this case, we're analyzing echoes from the universe's own first breath. Perhaps most poetic of all, this ancient light continues arriving at Earth every moment, carrying memories from when the cosmos was younger than a human lifetime. Every second, photons that have traveled for nearly 14 billion years wash over our planet, passing through our bodies and carrying within their wavelengths the story of how darkness gave birth to light, how invisible matter shaped the visible universe, and how the tiniest imperfections in cosmic uniformity became the galaxies, stars, and worlds that make up our cosmic home. The cosmic microwave background serves as both the universe's autobiography and its most ancient portrait, demonstrating that dark matter wasn't a late addition to cosmic architecture. It was there from the beginning, quietly shaping the framework upon which all subsequent structure would grow. Those tiny ripples preserved in light that has traveled across most of cosmic history now guide us naturally toward understanding how that invisible framework transformed from gentle fluctuations into the magnificent cosmic web of dark matter halos where galaxies would eventually find their homes. Those ancient ripples preserved in the cosmic microwave background, tiny temperature variations that mark the first stirrings of structure in an otherwise uniform universe, now guide us forward through cosmic time to witness one of the most elegant transformations in all of natural history. As the universe continued expanding and cooling beyond that pivotal moment when light finally broke free from matter, those microscopic fluctuations began their slow, patient evolution into the magnificent cosmic architecture we observe today. The invisible scaffolding that dark matter had started building in the universe's infancy was about to become the foundation upon which all luminous beauty would eventually rest. By the time the universe reached a few 100 million years in age, the cosmic microwave background had faded into the distance, becoming the faint whisper we detect today, and darkness once again ruled the cosmic stage. But this was not the empty, barren darkness that our everyday experience might suggest. Instead, it was a darkness pregnant with invisible potential, filled with ghostly structures already taking shape beneath the surface of perception, guided by gravity's patient hand working through dark matter particles that had been drifting and gathering since the universe's earliest moments. Dark matter had enjoyed a crucial head start. During those seemingly quiet eons, freed from any interaction with the electromagnetic chaos that had dominated the universe's bright infancy, while ordinary matter remained trapped in the cosmic microwave background's brilliant glow, unable to clump together due to radiation pressure that scattered atoms like leaves in a cosmic windstorm. Dark matter particles had been responding solely to gravity's gentle but persistent pull. They began gathering in regions where those primordial density fluctuations had created slightly more mass than the cosmic average, slowly forming what would become the invisible foundation stones of cosmic architecture. These concentrations of dark matter grew through a process both simple and profound, following the basic principle that mass attracts more mass like snowdrifts accumulating along a quiet fence line. Where dark matter had begun to accumulate, its gravitational influence reached outward like invisible hands, drawing in additional particles from the surrounding regions. Over millions and billions of years, these modest concentrations evolved into enormous, roughly spherical structures called dark matter, halos, vast cocoons of invisible matter that would eventually become the gravitational homes for the luminous galaxies we observe today. If you could have witnessed this epoch of cosmic evolution with eyes sensitive to dark matter's presence, you would have seen the universe filling with ghostly spheres of various sizes, completely invisible to any form of electromagnetic radiation, yet brimming with gravitational potential. These halos formed a kind of cosmic hierarchy, with smaller structures appearing first and then merging over time to create progressively larger and more massive gravitational wells, building cosmic architecture from the shadows outward in an elegant assembly process that continues even today. Into these carefully prepared gravitational wells, ordinary matter, primarily hydrogen and helium gas left over from the Big Bang, began its own patient descent. As this primordial gas encountered the dark matter halos, it started falling inward under the influence of their invisible gravity, cooling as it compressed and beginning to fragment into the dense clumps that would eventually ignite as the universe's first stars. The gas didn't simply pool like water finding the bottom of a container. Instead, it began swirling and compressing, conserving angular momentum while radiating away energy through simple molecules like hydrogen, the only cooling mechanism available in a universe not yet enriched with heavier elements. Where compression became strong enough and temperatures reached critical thresholds, the first stars flickered to life, igniting in the dark like embers catching fire in a vast, silent hearth. These primordial stars lived fast and luminous lives, burning with ferocity and ending in brilliant deaths that seeded their surroundings with heavier elements, carbon, oxygen, iron, the very ingredients that future generations of stars would use to cool more efficiently and that planets would one day weave into rock and life. With each cycle of stellar birth and explosive death, the universe improved its own ability to build structure, while the dark matter wells provided the stable gravitational framework within which this cosmic enrichment could occur. In a deeply poetic sense, dark matter played the role of the patient potter, and the visible universe became the clay. The invisible sculptor shaped, supported, and steadied the cosmic form, while never revealing its own hand, guiding the flow of matter and the rhythm of star formation with quiet dignity. Without dark matter's gravitational guidance, this elegant process of galaxy formation would have been far slower, messier, and significantly less efficient. Galaxies might never have formed in such abundance, and the night sky we gaze upon today would likely be a much lonelier, emptier place. The assembly of structure followed a hierarchical pattern that computer simulations can now reproduce with stunning accuracy. Small halos formed first, then merged to create larger ones in gravitational dances that could last billions of years. When two halos encountered each other, their dark matter components, being largely collisionless, would pass through each other almost without interaction, eventually settling into new, more massive configurations. Meanwhile, the gas within each halo would experience more dramatic interactions, crashing together, heating up, shocking, and then cooling again, sometimes triggering intense bursts of star formation that could be seen across cosmic distances. This ongoing process created a universe where structure grew from the bottom up, with every galaxy finding its home within a dark matter halo that extended far beyond the luminous regions where stellar activity took place. Even today, billions of years after this process began, our own Milky Way sits at the center of a massive dark matter halo that extends hundreds of thousands of light years beyond the visible stellar disk, continuing to capture and absorb smaller structures that venture too close to its gravitational influence. The relationship between dark matter halos and their luminous contents reveals one of the universe's most elegant partnerships. The halos dictate how fast galaxies can rotate, how much gas they can retain, and how they interact with their cosmic neighbors. Even tiny dwarf galaxies orbiting giants like the Milky Way owe their survival to dense knots of dark matter at their cores. Without this invisible glue, their weak gravity would be insufficient to prevent them from being torn apart by tidal forces. The cosmic web, with its intricate network of filaments and nodes, acted as the highway system connecting these halos, channeling gas along invisible threads and feeding the growing galaxies like rivers nourishing valleys. Each halo became a basin at the junction of these streams, collecting material and transforming it into the light we now observe. In regions where multiple filaments converged, galaxies grew bright and massive, while in quieter corners of the cosmic web, star formation proceeded at a more leisurely pace, creating the diverse population of galactic types we see today. As we trace this cosmic story from the first faint ripples through the formation of dark matter halos and the birth of the first stars, we find ourselves naturally drawn to examine these invisible cocoons more closely, to understand how every galaxy, including our own, lives suspended within vast spheres of unseen matter that continue to shape cosmic evolution through their patient, invisible influence. As we trace the cosmic story from those first faint ripples in ancient light through the patient assembly of invisible scaffolding, we arrive at one of the universe's most elegant and mysterious architectural achievements. Every galaxy in existence, no matter how brilliant its stars or graceful its spiral arms, lies nestled within a vast, invisible cradle, a roughly spherical cocoon of dark matter that extends far beyond the luminous regions where stellar fire burns and planets orbit in their quiet dances around distant suns. Picture, if you will, a small lantern suspended at the center of an enormous glass sphere, its warm glow illuminating only the tiniest fraction of the transparent globe that surrounds and protects it. This is the true nature of every galaxy. The stars, gas clouds, and all the glowing phenomena that capture our imagination through telescope images occupy merely the central region of these vast gravitational domains, while the dark matter halo stretches outward like an invisible cathedral built to house and steady the delicate flame of cosmic light. The halos surrounding our own Milky Way exemplifies the staggering scale of these structures. While the visible galaxy spans approximately 100,000 light-years from edge to edge, already an almost incomprehensible distance, the dark matter halo enveloping, it reaches perhaps 10 times farther into space, creating a sphere of gravitational influence so vast that it's already beginning to overlap with the halo of our nearest major neighbor, the Andromeda Galaxy. These two cosmic cities have been swimming in each other's invisible atmospheres for billions of years, their halos mingling in the darkness long before their luminous cores will eventually merge. This invisible majority doesn't consist of atoms, dust, or any familiar form of matter, but rather of dark matter particles moving in vast, stable swarms that orbit under their shared gravitational attraction. Unlike ordinary gas molecules that can collide and stick together, these ghostly particles pass through one another almost without interaction, creating a stable, diffuse cloud of mass that maintains its structural integrity across cosmic time. The halo's mass dominates the gravitational landscape so completely that it outweighs all visible matter by factors of 10 or more, providing the steady gravitational foundation that has supported galactic evolution for billions of years. The concept of these halos emerged naturally from Vera Rubin's pioneering observations of galaxy rotation curves. When she discovered that stars on the outskirts of galaxies move far too quickly to be bound by visible matter alone, the most elegant explanation was that each galaxy must reside within an extended reservoir of unseen mass. Once astronomers included these invisible halos in their calculations, the rotation curves flattened exactly as observed. The galaxies maintained their structural integrity, and the universe suddenly became beautifully self-consistent, These gravitational wells act like cosmic basins carved deep into the fabric of space-time. Within them, stellar orbits are gently guided and redirected, their restless energies transformed into coherent motion that can persist for billions of years. This is why galaxies don't simply scatter and dissolve over time, even though their constituent stars may be racing through space at hundreds of kilometers per second. The halo's gravity serves as an invisible net, catching wayward stars, bending their paths, and turning seemingly chaotic motions into the elegant, stable orbits we observe today. Beyond holding galaxies together, these dark matter cocoons also serve as gravitational anchors for smaller companions, the faint dwarf galaxies that orbit larger systems like fireflies around a cosmic campfire. Our Milky Way hosts dozens of these diminutive satellites, each tracing its own slow, looping path through our galaxy's vast invisible ocean. Some contain only a few thousand stars, yet remain gravitationally bound because the halo's influence reaches far enough to prevent their escape into the lonely depths of intergalactic space. Sometimes this gravitational embrace becomes a gentle dismantling. When a dwarf galaxy strays too close to a massive halo, tidal forces begin pulling it apart, stretching its stars into long, graceful ribbons called stellar streams. These luminous trails wind across the sky like cosmic calligraphy, each one a scar that reveals the shape and strength of the invisible gravitational landscape through which it flows. The most famous example is the Sagittarius stream. Created by a small galaxy currently being absorbed by our Milky Way, its arc of scattered stars serving as a glowing map of our halo's hidden contours. When galaxies encounter one another in their slow cosmic dances, their halos meet first, overlapping and blending long before the stellar components ever interact. These merging halos act like soft cushions, absorbing the initial gravitational impact and guiding the galaxies through their billion-year courtship toward eventual coalescence. What appears in telescope images as dramatic galactic collisions are actually graceful choreographies guided by the patient rules of invisible matter, transforming potentially catastrophic encounters into elegant cosmic ballets. The halos also regulate the very metabolism of galactic life. Gas falling into a halo from intergalactic space gets heated as it descends the gravitational well, creating a warm, diffuse atmosphere that must cool before condensing into new stars. The delicate balance between gas inflow and outflow, mediated by the halo's gravitational influence, determines whether a galaxy continues forming stars actively or gradually fades into quiet dormancy. In this sense, each halo acts like a cosmic thermostat, controlling the temperature and density conditions that govern how galaxies evolve and age. Despite their fundamental importance, these structures still hold mysteries that continue refining our understanding. Computer simulations often predict halos with sharply peaked central regions, yet some observations suggest gentler, flatter cores instead. This core cusp problem hints that either dark matter behaves in subtly different ways than our simplest models assume, or that ordinary matter, through energetic processes like supernova explosions, gradually reshapes the inner halo structure over cosmic time. As we contemplate these invisible cradles that hold every galaxy in their patient embrace, we find ourselves naturally drawn to examine our own cosmic neighborhood more intimately. We live deep within one of these vast spheres, carried along by gravitational currents that stretch across hundreds of thousands of light years, swimming unknowingly through the dark matter, sea that shapes our galaxy's destiny and guides our solar system's journey through the stars. From contemplating the vast invisible cradles that hold galaxies throughout the universe, our journey now draws us gently inward to the familiar spiral of our own cosmic home. The Milky Way, that shimmering band of starlight that arches across our night sky like a celestial river, represents far more than the beautiful sight that has inspired human wonder for millennia. What we observe from Earth, those countless stars painting luminous rivers across dark summer nights, occupies merely the glowing heart of something far more vast and mysterious, an immense invisible sphere that extends hundreds of thousands of light years beyond the furthest visible stars. We are not distant observers studying this phenomenon from afar, but intimate participants swimming in the very cosmic ocean we seek to understand. Every breath you take, every heartbeat, every photon of starlight that has ever touched your eyes occurs deep within the Milky Way's enormous dark matter halo, surrounded completely by invisible currents that have been flowing for billions of years. This ghostly cathedral encompasses us like a translucent bubble so vast that its edges already mingle with the halo of our nearest major neighbor, the Andromeda Galaxy, their invisible atmospheres, brushing together across the cosmic void long before their luminous cores will eventually merge. The dark matter surrounding us doesn't announce its presence through any sensation we can perceive. There is no cosmic wind pressing against our atmosphere, no resistance to planetary motion, not even the faintest ripple to suggest we're moving through anything substantial. Yet its gravitational influence quietly shapes every aspect of our galactic existence, providing the steady foundation that has supported our solar system's stable configuration for more than 4 billion years. This invisible ocean neither pushes nor pulls directly on the atoms composing our bodies, but it defines the gravitational landscape through which everything in our cosmic neighborhood moves with elegant precision. Our Sun, carrying the entire solar system in its gravitational embrace, races around the galaxy's center at approximately 220 kilometers per second, fast enough to circle Earth's equator in less than 3 minutes. This tremendous velocity carries us through the Milky Way's dark matter halo, like a ship sailing across calm, invisible waters, gliding through currents of unseen matter that stretch in all directions beyond our ability to perceive directly. Every 230 million years, our solar system completes one full orbit around the galactic center, a cosmic year that has repeated roughly 17 times since Earth first formed from swirling dust and gas. If we could somehow make this invisible substance visible, we would witness a faint spherical glow extending far beyond the bright spiral arms, reaching well past the furthest known stars like ghostly fingers, touching across the cosmic void. The visible Milky Way, all its glittering stars, vibrant nebulae, and tightly bound clusters, would appear as a small, luminous candle flickering at the very heart of a vast, silent glass sphere, making the familiar band of light we trace across our night sky seem almost insignificant by comparison. For astronomers studying this invisible ocean from within, the challenge resembles trying to chart the depths of a transparent sea using only the movements of ships sailing across its surface. They cannot observe the dark matter directly, but they can meticulously trace how stars, gas clouds, and smaller satellite galaxies move under its gravitational influence, gradually building a picture of the underlying mass distribution like oceanographers charting water flows by tracking floating debris carried by hidden currents, one of the most beautiful and revealing tools for mapping our galactic halo comes from studying stellar streams, those graceful ribbons of stars that wind across the sky like cosmic calligraphy. These luminous trails form when smaller galaxies or globular clusters venture too close to the Milky Way and are gradually torn apart by tidal forces, their stars spilling out along orbital paths that trace the gravitational contours of our invisible surroundings. Each stream serves as a glowing map of the dark matter landscape, curving and twisting according to the halo's hidden architecture. The most famous example is the Sagittarius stream, created by a small galaxy currently being absorbed by our own. Its long arc of scattered stars wraps around us like a ghostly ribbon, whispering tales of gravitational encounters that occurred hundreds of millions of years ago. Another delicate thread called GD1 stretches across the sky, its gentle kinks and gaps hinting at clumps of unseen mass it may have brushed along the way. These streams act like seismographs written in starlight, their subtle disruptions revealing the texture and distribution of dark matter throughout our galactic neighborhood. From these patient observations, we've learned that the Milky Way's halo possesses intricate structure, dense knots where smaller halos have merged with ours, gentle gradients reflecting our galaxy's formation history, and subtle ripples caused by gravitational interactions with passing neighbors. It's a reminder that even the dark is dynamic, constantly evolving and shifting with cosmic time, each disturbance leaving lasting fingerprints that persist for billions of years. Though we drift within this vast unseen realm, dark matter touches us in the most gentle way imaginable. Its particles pass effortlessly through Earth, through your body, through the walls around you, without ever interacting with ordinary matter except through gravity's honest influence. Right now, trillions of these ghostly visitors may be streaming through your body every second, yet you remain completely unaware of their passage. Rather than feeling unsettling, this realization brings a certain peace. We are carried along by currents that neither disturb nor demand attention, simply providing the invisible foundation upon which all cosmic architecture rests. The halo's gravity serves as the quiet guardian that keeps our galaxy stable, ensuring that stars near the galactic edge orbit just as securely as those closer to the center. Without this invisible anchor, the outer regions would drift away and dissolve into intergalactic space like smoke dissipating in a gentle breeze. It acts as a gravitational net, catching and retaining the dozens of small satellite galaxies that orbit the Milky Way, each one held in place by the same invisible influence that guides our solar system's motion through space. This dark matter ocean also regulates our galaxy's metabolism, controlling how gas from intergalactic space falls into the galactic disk and condenses into new stars. The delicate balance between heating and cooling, mediated by the halo's gravitational influence, determines whether star formation proceeds at a steady pace or erupts in dramatic bursts. In this sense, our invisible surroundings act like a cosmic thermostat, setting the conditions that have allowed our galaxy to evolve and age gracefully over billions of years. As we contemplate our position within this vast structure, swimming unknowingly through currents that stretch across hundreds of thousands of light years, we find ourselves naturally curious about the fundamental nature of this invisible sea. The same gravitational evidence that reveals the halo's presence also tells us it cannot consist of ordinary matter, not faint stars, cold gas, or cosmic dust. Having ruled out all familiar suspects through careful observation, we must venture into more exotic territory, seeking the fundamental particles that might compose this ghostly ocean through which we sail, surrounded always by the gentle presence of the unseen. Swimming within this vast invisible ocean that encompasses our galactic home, surrounded by gravitational currents that stretch across hundreds of thousands of light years, we find ourselves confronting the most fundamental question in our cosmic detective story. The evidence for dark matter's existence had become overwhelming: galaxy rotation curves, gravitational lensing, the cosmic web's architecture, and ancient whispers in the microwave background all pointed toward the same inescapable conclusion. Something unseen was providing the gravitational scaffolding that holds the universe together. But before physicists could venture into exotic realms of theoretical particles, they first had to ask the most reasonable question of all: could this mysterious mass simply be something familiar that had somehow escaped our notice? This approach represented the essence of good scientific methodology, systematically eliminating the obvious possibilities before embracing more revolutionary explanations. Perhaps the missing mass wasn't mysterious at all, but merely ordinary matter hiding in forms too faint, too cold, or too distant for our telescopes to detect. The cosmos is unimaginably vast, After all, and our instruments, however sophisticated, remain fundamentally limited in their reach and sensitivity. The first suspects were the shy members of the stellar family, objects that possessed substantial mass but produced little or no light. Astronomers imagined galactic halos populated by countless brown dwarfs, those failed stars that never gathered enough mass to sustain nuclear fusion, glowing feebly in infrared wavelengths but remaining invisible to optical surveys. Ancient white dwarf stars, the burned-out remnants of once brilliant suns that had exhausted their nuclear fuel and cooled beyond detection, seemed equally promising candidates. Even rogue planets, massive worlds ejected from their birth systems during chaotic formation processes, could drift through interstellar space like invisible wanderers, contributing their gravitational influence while remaining hidden from direct observation. Collectively, these hypothetical objects earned a memorable acronym that reflected both scientific precision and characteristic astronomical humor: MACHOs, or Massive Compact Halo Objects. The name captured perfectly what researchers were seeking: substantial masses concentrated in compact forms, lurking unseen within the dark matter halos that surrounded every galaxy. Testing the MACHO hypothesis required ingenious observational strategies. Direct searches for faint objects pushed telescope technology to its limits, but consistently fell short of finding sufficient numbers to explain the missing mass. Even the most sensitive infrared surveys designed to detect the faint heat signatures of brown dwarfs and cooling white dwarfs discovered far too few objects to account for the tenfold mass deficit revealed by galaxy rotation curves. More cleverly, astronomers employed gravitational microlensing, a technique that could reveal invisible objects through their gravitational effects rather than their light. When a massive object passes directly between Earth and a background star, its gravity acts like a natural lens, temporarily brightening the distant star's light in a characteristic pattern. Dedicated survey projects with names like MACHO, EROS, and OGLE monitored millions of stars in the Magellanic Clouds and toward the galactic center, watching patiently for these telltale flickers that would betray the presence of dark, compact objects. The results, accumulated over years of meticulous observation, painted a clear and disappointing picture for MACHO enthusiasts. While these surveys did detect occasional microlensing events confirming that some compact objects exist in galactic halos, their frequency was far too low to explain the missing mass problem. Even the most generous estimates, assuming maximum possible populations of brown dwarfs, white dwarfs, and rogue planets, fell short of the required mass by enormous factors. You could fill every corner of a galaxy with these faint objects and still account for only a small fraction of what the gravitational evidence demanded. With stellar remnants largely eliminated, attention turned to interstellar gas, vast reservoirs of hydrogen and helium that might be floating invisibly through galactic halos. Cold hydrogen, if sufficiently frigid, could avoid producing the characteristic radio emissions that normally reveal its presence. Perhaps galaxies were wrapped in enormous cocoons of this primordial gas, providing the extra gravitational influence while remaining hidden from electromagnetic detection. But cold gas, despite its name, cannot remain completely invisible indefinitely. It interacts subtly with cosmic rays and background ultraviolet radiation, producing faint but detectable emissions at specific radio wavelengths, particularly the famous 21-centimeter line of neutral hydrogen. When radio astronomers searched for these signals with increasingly sensitive instruments, they found some diffuse gas as expected, but nowhere near the quantities required to solve the dark matter puzzle. The halos weren't filled with cold hydrogen. They were genuinely, stubbornly dark in ways that ordinary gas simply couldn't achieve. Cosmic dust presented another initially attractive possibility. Space contains vast quantities of tiny grains composed of carbon, silicon, and other heavy elements, forged in stellar cores and scattered through the interstellar medium. These microscopic particles excel at absorbing and scattering visible light, And perhaps the universe was simply dustier than astronomers had realized, with enormous clouds of fine particles providing gravitational influence while hiding behind their own opacity. This hypothesis faced a fundamental flaw rooted in basic physics. While dust grains absorb visible light efficiently, they also re-radiate that absorbed energy at longer infrared wavelengths, glowing faintly but detectably in thermal emission. If the cosmos contained enough dust to account for dark matter's gravitational effects, the night sky would exhibit a noticeable infrared background glow that space-based telescopes could easily measure. Comprehensive infrared surveys, including observations by satellites like COBE and Spitzer, found no such pervasive emission on the scales required, definitively ruling out dust as a significant contributor to the missing mass. Black holes represented perhaps the most exotic of the conventional suspects, and for a time they seemed to satisfy all the necessary criteria. These gravitational monsters are completely invisible to electromagnetic radiation. They concentrate enormous masses in tiny volumes, and they could theoretically exist in vast numbers throughout galactic halos without direct detection. The universe might harbor swarms of black holes ranging from stellar masses down to much smaller primordial black holes that could have formed during the universe's earliest moments through the collapse of dense regions shortly after the Big Bang. Yet even black holes, despite their mysterious nature, could not hide in the numbers required to explain dark matter. If galactic halos consisted primarily of stellar mass black holes, they would produce frequent gravitational microlensing events as they passed in front of background stars, far more than observations actually detect. Large black holes would also generate persistent gravitational wave signals as they merged with one another, creating a cosmic background hum that sensitive detectors like LIGO and Virgo could easily hear. The absence of this signal places strict upper limits on how many massive black holes can populate the universe. Furthermore, the early universe itself provides fundamental constraints on how much ordinary matter can exist in any form. During the first few minutes after the Big Bang, when temperatures and densities were extreme enough to sustain nuclear fusion on cosmic scales, the universe forged a specific mixture of light elements, hydrogen, helium, deuterium, and lithium, in proportions that depend precisely on the total amount of ordinary matter present. This process, called Big Bang nucleosynthesis, acts like a cosmic recipe that limits the universe's baryon content to approximately 5% of the total mass energy budget. No matter how cleverly we hide ordinary matter in failed stars, cold gas, cosmic dust, or black holes, the fundamental physics of the early universe restricts how much can possibly exist. When astronomers carefully account for all the baryons they can find in stars, gas clouds, and other visible forms, the total approaches this theoretical limit, leaving no room for vast hidden reservoirs of ordinary matter to explain dark matter's gravitational effects. Step by step, methodical observation had systematically eliminated every conventional explanation. Each promising candidate, when subjected to rigorous scrutiny, failed to bridge the enormous gap between visible matter and the gravitational influences observed throughout the cosmos. It was as though cosmic detectives had illuminated every possible hiding place with the brightest searchlights available, only to find the shadows still deeper and more extensive than any ordinary substance could create. This process of elimination proved both humbling and profoundly exciting. Humbling because it demonstrated the limits of our initial assumptions about cosmic composition, but exciting because these very failures constituted powerful evidence pointing towards something genuinely unprecedented in human experience. The darkness wasn't an illusion, measurement error, or oversight in cosmic accounting. It was a clear signal indicating that the universe contained matter operating according to entirely different rules from every atom, molecule, and particle in the familiar world. scientists began to realize that dark matter must be fundamentally distinct from ordinary matter in every significant way. It doesn't interact with electromagnetic radiation, doesn't clump into stars or planets, doesn't heat up or cool down through familiar processes, and reveals itself only through gravity's honest testimony about the presence of mass. By every measure, it represents a completely separate category of matter, one that shapes the visible universe from shadows while remaining forever aloof from the electromagnetic interactions that define our everyday experience. This conclusion marked a revolutionary turning point in our understanding of cosmic architecture. The universe, it became clear, rests upon dual foundations: the familiar atomic matter that forms stars, planets and living beings, and a second, silent component that provides the gravitational framework supporting all visible structures. Without dark matter's invisible influence, galaxies wouldn't form, stars wouldn't maintain stable orbits, and the cosmos might appear flat and featureless rather than rich with the intricate beauty we observe across the night sky. Having methodically ruled out every ordinary explanation, the mystery deepened into something far more profound and exciting. If conventional matter couldn't account for dark matter's pervasive effects, then the universe must be concealing a deeper secret, one that would lead physics and astronomy down entirely new paths of discovery, from underground laboratories buried beneath mountains to massive particle accelerators probing the fundamental building blocks of reality itself. The stage was now perfectly set for the next phase of our cosmic investigation. If dark matter wasn't made of ordinary atoms, what exotic particles might compose this ghostly ocean through which we sail, surrounded always by the gentle presence of the invisible and the unknown? Having turned every cosmic lantern toward the familiar and found only deeper shadows stretching beyond our instrument's reach, the great detective story of dark matter now pivoted toward a more profound realization. The systematic elimination of every ordinary explanation, failed stars, cold gas, cosmic dust, and even black holes, had revealed something far more extraordinary than a simple oversight in our celestial census. The universe was clearly concealing a secret that transcended the boundaries of known matter entirely, harboring vast quantities of mass that operated according to fundamentally different rules from every atom and molecule in the familiar world around us. With conventional physics exhausted, scientists found themselves compelled to venture into the realm of truly exotic possibilities, imagining particles so elusive they could fill the cosmos while remaining completely invisible to every form of electromagnetic radiation. If this ghostly ocean surrounding us possessed substance, then somewhere in nature's hidden catalogue there must exist building blocks meeting a remarkably specific and demanding job description, particles that could provide the gravitational scaffolding, holding galaxies together while never once betraying their presence through light, heat, or collision. The requirements for these hypothetical dark matter particles read like a cosmic want ad written by the universe itself. First, they must be cold, meaning they move relatively slowly through space so that gravity can gather them into the clumps and filaments we observe throughout the cosmic web. Particles racing around at near light speed would be too restless to settle into the stable structures that cradle galaxies, their kinetic energy preventing the patient accumulation of mass that cosmic architecture demands. Second, these particles must possess extraordinary stability, capable of surviving unchanged for billions of years without decaying into lighter fragments that might reveal themselves through detectable radiation. The persistent influence of dark matter throughout cosmic history, from the universe's earliest structural formation to today's spinning galaxies, requires a particle that is essentially immortal on cosmological timescales, as enduring as the cosmos itself. Third, and perhaps most crucially, they must be remarkably shy, interacting with ordinary matter only through gravity's gentle pull while remaining aloof from all the electromagnetic forces that govern our everyday experience. This explains their ghostly nature. They don't absorb or emit light. They don't heat up or cool down through familiar processes, and they pass through planets, stars, and even our bodies as if we weren't there, leaving behind only the honest testimony of their gravitational influence. Nature had already provided tantalizing hints that such elusive particles could exist. Neutrinos, those ghostly messengers streaming from nuclear reactions in stellar cores, already demonstrate many of these characteristics. They possess tiny masses, rarely interact with ordinary matter, and can slip through entire planets without leaving any trace of their passage. Trillions of neutrinos from the Sun flow through your body every second, yet you remain completely unaware of their journey. Unfortunately, neutrinos move too quickly and weigh too little to account for dark matter's gravitational effects, representing hot, dark matter that would have prevented galaxies from forming in the early universe. The cosmos needed something heavier, cooler, and more patient, particles that could gather quietly under gravity's influence while maintaining their electromagnetic invisibility. This realization led physicists to propose their first and most celebrated candidate, the WIMP, or Weakly Interacting Massive Particle. The name itself captures the essence of what researchers were seeking: substantial masses that interact only through gravity and possibly the weak nuclear force, the same fundamental interaction responsible for certain types of radioactive decay. WIMPs emerged naturally from elegant extensions of particle physics, particularly supersymmetry theories that predict entire families of yet undiscovered particles hiding just beyond our current experimental reach. In these theoretical frameworks, every known particle possesses a heavier superpartner with slightly different properties. Most of these hypothetical companions would be unstable and decay rapidly, but the lightest supersymmetric particle would have nowhere to go. Conservation laws would protect it from destruction, creating a stable relic that could survive from the universe's earliest moments to the present day. These WIMPs could have formed abundantly in the hot, dense conditions shortly after the Big Bang, when temperatures were high enough for all types of particles to be created and destroyed in constant thermal equilibrium. As the universe expanded and cooled, most WIMP pairs would have found each other and annihilated back into energy, but a small fraction could have survived this cosmic winnowing process. Those survivors would still be drifting through space today, invisible remnants of the primordial fireball carrying within their collective mass the gravitational blueprint of cosmic structure. The appeal of WIMPs extends beyond their theoretical elegance to encompass what physicists call the WIMP miracle, a beautiful cosmic coincidence where the same properties that make these particles excellent dark matter candidates also predict they should have been produced in precisely the right quantities during the early universe to account for the dark matter we observe today. It's as if the cosmos had fine-tuned its particle physics to solve multiple fundamental problems simultaneously. From an entirely different corner of theoretical physics emerged another compelling candidate that seemed to arise almost by accident. The axion wasn't originally conceived to solve the dark matter puzzle at all, but was proposed in the 1970s to address a subtle but fundamental problem in quantum chromodynamics, the theory describing the strong nuclear force that holds atomic nuclei together. Physicists had noticed that certain symmetries in this theory should be violated in ways that experiments consistently failed to observe, suggesting some additional mechanism must be preserving nature's balance. The axion represents that mechanism, a quantum field permeating all of space, maintaining cosmic symmetry through its gentle oscillations. When this field vibrates, it behaves as though it's composed of particles, much like a violin string's continuous motion produces discrete musical notes. These axion particles would be extraordinarily light, perhaps 1 trillion times less massive than electrons. But they could exist in such staggering numbers that their collective gravitational influence would dominate the universe's mass budget. Unlike the relatively hefty WIMPs, axions would create a cosmic fog of countless lightweight particles filling every cubic centimeter of space with ghostly presence. They would interact with ordinary matter even more weakly than WIMPs, passing through entire galaxies without ever colliding with a single atom. However, they might occasionally transform into photons when passing through strong magnetic fields, a process so rare that detecting it would require exquisite experimental precision and years of patient observation, like tuning a cosmic radio to catch the faintest whisper from the dark. A third possibility emerged from the shadowy realm of neutrino physics: the sterile neutrino. Regular neutrinos already possess many dark matter-like qualities, but theoretical extensions predict additional types that would be even more reclusive, participating in no interactions except gravity itself. These sterile cousins would be completely invisible to electromagnetic and nuclear forces, making them perfect dark matter candidates if they possess sufficient mass. Depending on their properties, sterile neutrinos might constitute warm, dark matter, not quite as cold as WIMPs, but still capable of forming the large-scale structures we observe in the cosmic web. Some astronomical observations have even hinted at possible sterile neutrino signatures in X-ray emissions from galaxy clusters. Though these tantalizing clues remain tantalizingly ambiguous, always one careful analysis away from certainty. Each of these candidates represents a different vision of the invisible universe surrounding us. WIMPs would be like scattered boulders of unseen matter, relatively heavy particles distributed sparsely through space. Axions would resemble a pervasive mist, countless lightweight particles creating a soft, cosmic fog that fills every corner of existence. Sterile neutrinos would occupy middle ground, substantial enough to clump into structures, but light enough to smooth out smaller-scale variations in the cosmic web. The universe might even contain multiple types of dark matter, a complex ecosystem of invisible particles working together to provide the gravitational scaffolding we observe. Different species could dominate at different scales or in different cosmic epochs, creating a rich tapestry of unseen matter that we're only beginning to understand through its collective gravitational influence. What unites all these candidates is their shared commitment to cosmic shyness. They're cold enough to move slowly and clump under gravity's patient influence, stable enough to survive since the universe's youth, and antisocial enough to avoid electromagnetic interactions that would reveal their presence. These qualities allow them to serve as the universe's invisible architects, shaping cosmic structure without ever stepping into the spotlight of human observation. There's something almost whimsical about imagining the cosmos filled with these ghostly marbles rolling endlessly through matter, occasionally brushing past atoms without a sound. We are surrounded by them, bathed in them, swimming through their invisible currents, yet they pass through us like wind through mist. These dark matter candidates are cosmic phantoms, perfectly polite guests who never disturb the furniture but quietly hold the entire house of the universe together. The search for these elusive particles has launched one of the most ambitious experimental programs in the history of science, requiring instruments of unprecedented sensitivity hidden in the quietest corners of our planet. If these invisible visitors are everywhere, as abundant as the ocean and as subtle as its deepest currents, then they must be passing through us even now, countless and patient, leaving only gravity's honest testimony in their wake. The question now facing humanity is both simple and daunting. If these particles are flowing through every cubic inch of space around us, how do we finally catch one in the act of existing? The answer lies in the most sensitive experiments ever conceived, hidden deep beneath mountains and ice, where scientists have set their patient watch, listening for the softest whisper that might finally give a name to the ghost that shapes our cosmos. These ghostly particles, whether massive WIMPs, ethereal axions, or elusive, sterile neutrinos, present us with perhaps the most daunting challenge in the history of experimental physics. If they truly flow through every cubic inch of space around us, passing through our bodies like cosmic phantoms in an endless, silent parade, then how do we finally catch one in the act of existing? The answer has led scientists to some of the quietest, most isolated sanctuaries on Earth, far from the electromagnetic chaos of our modern world, deep beneath mountains where the patient art of listening for the invisible has become humanity's most sensitive conversation with the cosmos. The fundamental principle behind direct dark matter detection sounds deceptively simple, though its execution demands engineering precision pushed to the very limits of human capability. If dark matter particles are indeed streaming through the universe in vast, invisible currents, then occasionally, perhaps once in a year of patient waiting, one might collide with an atomic nucleus within a carefully prepared detector. This wouldn't be a dramatic explosion or brilliant flash of light, but rather the faintest possible whisper, a single nucleus recoiling with barely measurable energy, like a billiard ball struck by an invisible cue moving at cosmic speeds. To hear such ethereal encounters, experiments must retreat far from the surface world's constant bombardment of cosmic rays and electromagnetic interference. Underground laboratories burrow deep into solid rock, using the Earth itself as a massive shield against the incessant shower of particles raining down from space. Some facilities descend nearly a mile beneath the surface, where the weight of overlying stone filters out all but the most penetrating radiation, creating pockets of unprecedented quiet where the subtlest whispers from the dark might finally be detected. The detectors themselves represent marvels of precision that border on the miraculous. Many employ tanks filled with ultra-pure liquid xenon, chosen for its remarkable properties as both target and sensor. When a dark matter particle strikes a xenon nucleus, the collision produces two distinct signatures, an immediate flash of ultraviolet light followed by a delayed cloud of electrons that drift upward through the liquid. This dual signal nature allows researchers to distinguish genuine nuclear recoils from the electronic interactions that create most background noise, like learning to recognize not just a sound, but the specific timbre that distinguishes a whispered secret from ambient murmur. Other experiments utilize crystalline detectors cooled to temperatures within thousandths of a degree of absolute zero, where even the faintest energy deposit would produce a measurable temperature increase or lattice vibration. These cryogenic calorimeters transform entire crystals of germanium or silicon into cosmic thermometers so sensitive they could register the heat from a single photon of light. The crystals are suspended in elaborate refrigeration systems, isolated from vibration and surrounded by multiple layers of shielding that create some of the most stable, quiet environments ever achieved in human technology. One of the leading experiments, the Lux Zeppelin detector, sits nearly a mile underground in a former gold mine in South Dakota's Black Hills, where solid rock provides natural protection from cosmic radiation. Its central chamber contains several tons of liquid xenon maintained at precisely controlled conditions, surrounded by photomultiplier tubes that can detect individual photons of scintillation light. When a dark matter particle occasionally collides with a xenon nucleus, the impact produces that characteristic double signature, a prompt flash followed by delayed electrons that helps distinguish genuine interactions from the countless mundane events that would otherwise overwhelm the signal the patients required. For these experiments extends far beyond normal human timescales, demanding a kind of meditative dedication to the art of cosmic listening. Detectors may operate continuously for years without recording anything that could confidently be attributed to dark matter, their electronic sentries maintaining constant vigilance while researchers spend much of their time eliminating false alarms. Every cosmic ray that penetrates the shielding, every trace of natural radioactivity in detector materials, every vibration from distant traffic must be identified and subtracted from the data, leaving only the profound quiet where genuine signals might finally emerge. This global network of underground sanctuaries spans the planet like a distributed instrument for touching the invisible. Italy's Gran Sasso National Laboratory houses multiple experiments in tunnels carved through the Apennine Mountains. Japan's Kamioka Observatory occupies a former zinc mine surrounded by nearly a mile of protective stone. Canada's SNO Lab extends 2 kilometers underground, while facilities in China, Australia, and elsewhere join this patient planetary vigil. Each represents a delicate balance between accessibility for researchers and isolation from the electromagnetic noise of modern civilization. The human dimension of these experiments carries its own quiet poetry. Scientists descend through mine shafts and mountain tunnels, walking into rooms where the air scrubs itself clean and the loudest sound might be the gentle hum of cooling systems. They tend their instruments like monks maintaining technological monasteries, recording data in careful logbooks while the world above continues its bustling existence, largely unaware of the deep watch being kept below. There's something profoundly moving about these small teams working in environments where the most significant events might be completely invisible to every sense except the patient accumulation of data in computer memories. The emotional landscape oscillates between profound patience and sudden excitement. Years of careful data collection create rhythms of quiet expectation, punctuated by occasional moments when unusual signals appear in the data stream. Each anomaly triggers intensive analysis as teams of physicists examine every possible explanation, often spending months determining whether they've glimpsed something genuinely new or encountered a previously unrecognized form of background noise. The history of dark matter detection includes tantalizing moments when experiments reported potential signals that briefly captured the scientific community's imagination, only for further analysis to reveal more mundane explanations. Yet even the silence carries scientific value. Each year, without a clear detection, helps constrain the properties that dark matter particles might possess, gradually narrowing the parameter space where they could be hiding and guiding the design of future experiments with even greater sensitivity. This cartography of absence represents not failure, but progress, the careful mapping of what is not, which inevitably leads toward what is. Looking toward the future, these underground experiments face an elegant challenge known as the neutrino flaw. Eventually, solar neutrinos and other astrophysical sources will create an irreducible background that no amount of shielding can eliminate, requiring even more sophisticated techniques to separate dark matter signals from this honest cosmic noise. It's a boundary that demands cleverer strategies, using directionality, timing, or target selection to continue listening when the universe itself begins to hum with unavoidable background. The underground laboratories maintain their patient vigil regardless of these challenges, their detectors accumulating data even when results seem to point toward null findings. Somewhere in the interplay between profound silence and careful listening, between the seen and unseen universe, truth is waiting. These experiments represent humanity's most direct attempt to touch the invisible scaffolding that holds the cosmos together, each photon of scintillation light carrying the possibility of bridging the gap between mystery and understanding. If the underground whispers continue their silence, perhaps the answer lies elsewhere in the cosmos, where natural processes might amplify these ghostly interactions into signals bright enough for our instruments to detect across the vast distances of space itself, while those patient underground sentinels continue their quiet vigil in Earth's deepest sanctuaries, listening for the softest whisper that might betray dark matter's direct touch. Our search for the invisible naturally lifts toward the vast theater of space itself, The universe has been conducting its own experiments for billions of years, far longer and on scales immeasurably grander than any human laboratory could achieve. Galaxies collide in slow-motion ballets across cosmic time. Particles interact in the dense hearts of stellar cores, and enormous clouds of dark matter overlap and merge in gravitational dances that dwarf our most ambitious earthbound efforts. Perhaps somewhere in all this quiet cosmic activity, dark matter particles might finally give themselves away, not through direct collision with our detectors, but through the faint byproducts of their invisible interactions with each other. This approach, known as indirect detection, represents a fundamentally different strategy for unveiling the hidden universe. Instead of trying to catch dark matter particles in the act of striking atomic nuclei in our underground chambers, scientists search the cosmos for possible consequences when these ghostly particles encounter and annihilate each other in the depths of space. It's rather like searching for footprints in cosmic sand rather than trying to glimpse the invisible creature itself. When two dark matter particles meet in their eternal wandering, theoretical models suggest they might transform into more familiar forms of matter and energy. High-energy gamma rays, exotic particles or streams of electrons and positrons that could travel across galactic distances. To reach our waiting telescopes, the most promising hunting grounds for these indirect signatures lie where dark matter concentrations reach their greatest density. The center of our own galaxy presents an ideal target, where computer simulations predict dark matter should be packed most tightly around the supermassive black hole that anchors the Milky Way's gravitational architecture. If dark matter particles occasionally find each other in this cosmic crowd and annihilate in brief flashes of energy, the galactic center should glow faintly with gamma rays, the most energetic form of electromagnetic radiation, carrying unmistakable signatures of the fundamental processes that created them. NASA's Fermi Gamma Ray Space Telescope, orbiting high above Earth's atmosphere, where it can detect these penetrating photons without interference, has indeed spotted something intriguing emanating from our galaxy's heart. An excess of gamma rays emerges from the galactic center that doesn't quite match what astronomers expect from known astrophysical sources like pulsars, black holes, or cosmic ray interactions. For a tantalizing period, this mysterious glow appeared to match theoretical predictions for dark matter annihilation with remarkable precision, its energy spectrum and spatial distribution aligning beautifully with what physicists had calculated for certain types of WIMP interactions. Yet, as is often the case in science, the universe proved more complex than initial interpretations suggested. The galactic center represents one of the most chaotic regions in our cosmic neighborhood, a crowded orchestra pit where every instrument competes for attention. Millisecond pulsars spin like cosmic lighthouses. Cosmic rays crash into interstellar gas, creating brief sparks of high-energy light, and magnetic fields conspire to complicate the background in ways that can mimic dark matter signatures. Teams have traced the signal this way and that, with some showing how populations of unseen pulsars could account for much of the excess, while others argue the statistics still favor dark matter's subtle hand. The glow remains, but the debate has softened its edges like firelight seen through fogged glass. Tempting, suggestive, yet not quite decisive. To escape this electromagnetic cacophony, astronomers turn their attention to quieter cosmic stages, the dwarf spheroidal galaxies that orbit the Milky Way like dim pearl beads scattered through space. These small companions possess a remarkable property that makes them ideal dark matter laboratories. They appear to consist almost entirely of invisible matter, with very little ordinary gas or stellar activity to complicate the analysis. Their skies hold fewer fireworks, their backgrounds remain gentler, their potential signatures cleaner. If dark matter annihilation glows anywhere, it should shine there with the straightforward honesty of a lantern in an empty room. One after another, Telescopes have gathered their faint light, stacking observations over years, hunting for collective whispers in the gamma-ray spectrum. Hints have appeared and receded like cosmic mirages. A slight uptick here, a promising energy contour there, and then with additional data, the footprints smooth back into statistical sand. The universe seems to whisper not here, or perhaps not yet, maintaining its patient reserve while our instruments grow ever more sensitive. Other cosmic messengers carry different potential clues. The Alpha Magnetic Spectrometer aboard the International Space Station has detected an unexpected excess of positrons, antimatter twins of electrons, arriving in cosmic rays. Such particles could be forged in the quiet collisions of dark matter, reaching us as emissaries from invisible meetings scattered throughout the galaxy. Yet pulsars can also shed positrons like embers spun from rapidly rotating wheels, and supernova remnants stir charged particles into confusing swarms. Disentangling these overlapping stories resembles trying to hear a single violin line in the middle of a cosmic thunderstorm. Not impossible, but demanding extraordinary precision and patience. Neutrinos, the universe's most incorruptible messengers, offer another window into dark matter's possible behavior. If these invisible particles accumulate in dense environments like the Sun's core, they might occasionally annihilate there, producing neutrinos that stream outward, unimpeded by magnetic fields or intervening matter. At the South Pole, the Ice Cube Observatory watches a cubic kilometer of Antarctic ice for the faint blue flashes that betray a neutrino's passage, listening with almost monastic calm to events that ignore every barrier. Thus far, our nearest star has not confessed to harboring such invisible meetings, and the broader sky maintains its counsel. Regarding dark matter's neutrino signatures, the fundamental challenge facing all these skyborne searches lies not in the scarcity of light, but in its overwhelming abundance. Space pulses with activity on every scale, pulsars tick like cosmic clocks, black holes flare like distant lighthouses, and shock fronts in supernova remnants scribble bright graffiti across interstellar walls. Cosmic rays, magnetic fields, and interstellar dust create backgrounds so rich that even genuine dark matter signals would arrive braided with more familiar threads. The science becomes an exercise in careful unweaving, asking whether each remaining strand represents simply an uncommon arrangement of known phenomena or the first silk from an entirely unseen cosmic loom. Yet this ambiguity proves scientifically fruitful rather than frustrating. Every anomaly, every almost signal refines our understanding of what dark matter could be. Each improved map of the galactic center narrows the parameter space where dark matter might hide. Every non-detection from dwarf galaxies tightens constraints on annihilation rates. Each positron spectrum and neutrino limit becomes another brushstroke in a larger portrait whose blank spaces prove as informative as the painted regions. New instruments promise to sharpen this cosmic view considerably. The Cherenkov telescope array, with its forests of mirrors designed to catch the brief blue breath of gamma rays cascading through Earth's atmosphere, offers unprecedented sensitivity and resolution. Future space missions continue refining their electromagnetic ears, teasing apart backgrounds with growing finesse and mapping the universe's gamma-ray glow with ever greater precision. There exists a delicate poetry in using light to find what refuses to shine, a paradox resolved not through contradiction but through elegant geometry. We cannot observe dark matter directly, but we can trace how it might shape the paths of brightness, where it could condense enough to transform invisibility into whispers of detectable photons. This approach honors patience above all else, treating ambiguity not as failure but as signposts pointing toward better questions and more sophisticated searches. If the cosmic whispers remain too faint for our current technology to decipher clearly, if the gamma rays maintain their double meanings and neutrinos arrive only from familiar stellar forges, then curiosity naturally leads us toward one final arena. Perhaps we cannot wait for the universe to reveal dark matter's secrets naturally. Perhaps we must recreate the violent conditions where these particles first emerged, using the controlled thunder of particle colliders to make the invisible briefly step into light's outline. If the universe's natural laboratories, those vast cosmic theaters where galaxies collide and dark matter halos merge across billions of years, continue to whisper their secrets in voices too faint for our current instruments to decipher clearly, then perhaps the time has come for humanity to take a more direct approach to this ancient mystery. Rather than waiting patiently for dark matter to reveal itself through the gentle touch of underground collisions or the ambiguous glow of distant gamma rays, physicists have turned toward one of our species' most audacious technological achievements, the ability to recreate, for fleeting instants, the violent conditions that existed when the universe was young enough for exotic particles to emerge from pure energy. This represents a fundamental philosophical shift in our cosmic detective work, moving from passive observation to active creation. Instead of hoping that the invisible will eventually announce itself through natural processes occurring on cosmic timescales, scientists now propose to manufacture these elusive particles directly, summoning them from the quantum vacuum through collisions so energetic they briefly restore the temperatures and densities that filled space during the universe's first moments. It's rather like shaking an enormous, intricate puzzle box in the hope that a missing piece, normally hidden in secret compartments, might momentarily tumble out and reveal its shape. Beneath the rolling countryside along the Franco-Swiss border, the Large Hadron Collider traces its magnificent 27-kilometer circle through bedrock, representing humanity's most powerful instrument for probing reality's fundamental architecture. Within its superconducting tunnels, protons, those familiar building blocks of atomic nuclei, accelerate to speeds approaching light itself, guided by magnetic fields so precise they can steer particles around gentle curves spanning multiple countries. When these cosmic bullets finally collide head-on within the hearts of cathedral-sized detectors, they recreate for infinitesimal moments the conditions that existed when the universe was less than a billionth of a second old. The logic underlying this search possesses an elegant simplicity rooted in one of physics' most fundamental principles, energy conservation. Like meticulous cosmic accountants, physicists know precisely how much energy enters each collision, and they can methodically catalogue every particle that emerges from the subatomic wreckage. If the energy ledger doesn't balance, if some fraction mysteriously vanishes without producing detectable debris, then that missing energy might have escaped in the form of particles that refuse to interact with any known detector. In essence, dark matter's calling card would be revealed not by what we observe, but by what we cannot account for. This approach transforms the search for invisible matter into an exercise in quantum bookkeeping. The detectors surrounding collision points represent some of the most sophisticated instruments ever constructed, layered like enormous onions with each shell designed to catch different types of particles. Charged particles leave delicate tracks in silicon sensors, photons deposit their energy in electromagnetic calorimeters, and hadrons interact within dense absorbers made of lead and steel. By the time any particle has passed through all these layers, it has either been measured, absorbed, or identified as something so weakly interacting it might as well be invisible. The ATLAS and CMS detectors, these underground cathedrals of science weighing thousands of tons each, record the aftermath of billions of collisions per second, creating torrents of data that challenge the very limits of computational analysis. Within this overwhelming stream of information, physicists search for the telltale signature of missing energy, events where the vector sum of all detected particles fails to add up to zero, indicating that something substantial has escaped unnoticed, carrying away its share of momentum and energy, yet finding genuine. Missing energy proves extraordinarily challenging amid the electromagnetic chaos of high-energy collisions. Many known particles, particularly neutrinos, routinely escape detection while carrying away substantial energy, creating backgrounds that must be carefully subtracted from any potential dark matter signal. The analysis becomes an art of distinguishing between expected forms of invisibility and genuinely anomalous disappearances that might herald new physics beyond our current understanding. Wiki search extends beyond simply looking for energy that vanishes without explanation. Theoretical frameworks suggest various ways dark matter might briefly materialize in these controlled explosions. A high-energy photon recoiling against empty space, a jet of particles balancing against nothing visible, or subtle deviations in the behavior of the Higgs boson each could indicate that invisible particles have momentarily stepped into existence before slipping back into quantum shadows. The discovery of the Higgs boson in 2012 demonstrated the LHC's remarkable capability to find particles that had been hiding in theoretical frameworks for decades, validating this approach to exploring physics beyond direct observation. This success naturally raised hopes that dark matter particles might reveal themselves through similar techniques, especially if they interact with the Higgs field or participate in the same symmetries governing other fundamental forces. Some theoretical models predict dark matter could be produced alongside the Higgs boson or through its decay, creating subtle correlations between visible and invisible particles that careful analysis might eventually uncover. Other frameworks suggest dark matter might interact through entirely new forces, mediated by particles that could themselves be produced and studied in collider experiments, providing indirect windows into reality's invisible sectors. Despite years of increasingly sophisticated searches, the LHC has not yet provided unambiguous evidence for dark matter production. Each new analysis refines the constraints on what forms dark matter might take, gradually eliminating regions of theoretical parameter space while pointing toward more subtle or exotic possibilities. This process of elimination proves scientifically valuable even without positive discoveries, helping theorists focus their attention on the most promising avenues for future investigation. The absence of clear signals doesn't necessarily indicate that dark matter lies beyond the LHC's reach. These particles might simply be heavier than current collision energies can produce, or they might interact so weakly that their production rates remain below detection thresholds, despite the collider's impressive capabilities. Future upgrades will increase both the energy and intensity of collisions, potentially accessing mass ranges and interaction strengths that current experiments cannot explore. There exists a profound beauty in using these moments of controlled violence, the most energetic collisions achievable by human technology, to search for something as serene and enduring as dark matter, which has been patiently sculpting cosmic architecture for billions of years. Each collision represents a brief moment when the universe's fundamental laws operate at their most extreme, creating opportunities for new physics to emerge from the quantum vacuum and potentially bridge the gap between visible and invisible components of reality. The philosophical elegance of collider searches lies in their direct approach to mystery. Rather than waiting for dark matter to reveal itself through gravitational effects or hoping to catch it in underground laboratories, these experiments attempt to compel the universe to show its hidden cards, using controlled thunder to illuminate what natural processes keep shrouded in darkness. They represent humanity's most ambitious attempt to force a conversation with the invisible, transforming absence into evidence through the honest testimony of energy conservation. Whether dark matter ultimately reveals itself through missing energy signatures, exotic particle cascades, or subtle deviations from expected behavior, the collider approach continues refining our understanding of what's possible in the unseen sectors of existence. Each collision is a question posed directly to the quantum vacuum, each analysis a careful listening for answers that might emerge from the controlled chaos of matter meeting antimatter at the very limits of physical possibility, even as these underground cathedrals continue their patient bombardment of matter against matter, searching for glimpses of what refuses to shine. The broader scientific community has begun contemplating an alternative explanation that would be equally revolutionary. Perhaps the mystery lies not in exotic particles at all, but in our understanding of gravity itself, a possibility that challenges us to consider whether the universe might be operating according to rules subtly different from those we've assumed, requiring us to rewrite not the cosmic inventory, but the very laws that govern how matter moves through space and time. Even as those underground cathedrals continue their patient bombardment of matter against matter, searching for glimpses of particles that refuse to shine, a quieter revolution has been brewing at the edges of theoretical physics, one that questions not what the universe contains, but the very rules by which it operates. For all the mounting evidence pointing toward vast quantities of invisible matter, a thoughtful minority of scientists has wondered whether we might be asking entirely the wrong question. Perhaps nothing is missing at all. Perhaps gravity itself, that most familiar yet mysterious of nature's forces, simply behaves differently on the vast scales where galaxies spin their slow waltzes and clusters drift through cosmic time. This alternative perspective emerged from a beautifully simple observation. If galaxies are spinning too fast and clusters are holding together too tightly, then either there's invisible matter providing extra gravitational pull, or gravity itself operates according to subtly different rules when applied to the gentle accelerations found at the edges of cosmic structures. It's rather like discovering that a familiar musical instrument produces unexpected harmonies when played in a grand concert hall. The same fundamental physics might express itself differently when the stage becomes sufficiently vast and the forces become whisper soft. The first serious exploration of this possibility came in the early 1980s from physicist Mordechai Milgram, who proposed something elegantly called modified Newtonian dynamics, or MOND for short. At the time, Vera Rubin's meticulous observations of flat galaxy rotation curves were revolutionizing astronomy, revealing that stars in galactic outskirts move far too quickly to be bound by visible matter alone. While most astronomers concluded that invisible mass must be providing the extra gravitational influence, Milgram wondered whether Newton's venerable laws, while perfectly accurate for falling apples and planetary orbits, might need gentle adjustment when applied to the extraordinarily weak accelerations experienced by stars orbiting thousands of light-years from galactic centers. In Milgram's elegant framework, gravity doesn't weaken exactly as Newton predicted when accelerations become vanishingly small, the kind of gentle tugs that govern motion at galaxy peripheries, where gravitational influences stretch across cosmic distances. Instead of following the familiar inverse-square relationship that works beautifully for solar system dynamics, gravitational acceleration tapers off more gradually, providing just enough extra influence to explain why outer stars don't drift away into intergalactic space. The remarkable appeal of MOND lies in how well it works for certain specific phenomena, often with startling precision. It can predict the rotation curves of many galaxies with impressive accuracy, sometimes capturing subtle details that even sophisticated dark matter simulations struggle to reproduce. Even more intriguingly, MOND naturally explains some fine-tuned relationships that puzzle dark matter theorists, such as the tight correlation between a galaxy's visible mass and its rotation speed, the baryonic Tully-Fisher relation. In MOND's universe, this pattern emerges directly from modified gravitational laws like music arising naturally from a well-tuned instrument, whereas dark matter models must carefully adjust invisible halo properties to achieve the same harmony. For a time, this alternative approach seemed to offer beautifully economical solutions to cosmic mysteries. Instead of populating the universe with exotic particles that stubbornly refuse to reveal themselves despite decades of increasingly sophisticated searches, MOND suggested we could solve everything with a single, elegant tweak to familiar physics. There's undeniable appeal in such theoretical parsimony. Why invent entirely new forms of matter when adjusting our understanding of gravity might accomplish the same goal with far fewer assumptions? Yet, as astronomers tested Mond's predictions across broader cosmic landscapes, the theory began revealing its limitations, like a map that works perfectly for city streets but struggles with mountain ranges and coastlines. While Mond proved remarkably successful for individual galaxies, it faltered when confronted with larger structures like galaxy clusters, where the gravitational binding requires far more extra influence than the theory's modifications can provide. Even this alternative approach finds itself invoking some form of unseen matter to hold the largest cosmic structures together, an ironic twist that undermines Mondi's fundamental promise of eliminating invisible mass. Entirely more challenging still, Mond faces significant difficulties explaining the precise patterns observed in gravitational lensing, particularly the dramatic evidence from collisions like the bullet cluster. When two galaxy clusters crashed together, the hot gas, representing most of the visible matter, slammed into itself, slowed down, and glowed brightly in X-rays. Yet lensing maps revealed that the bulk of the gravitational mass had sailed through the collision largely unaffected, creating a clear spatial separation between visible matter and gravitational influence. This clean divorce between light and mass fits naturally within the dark matter picture, where collisionless invisible halos glide past each other while ordinary matter experiences electromagnetic interactions. Mond, as a modification of gravity rather than matter, struggles to explain why gravitational effects should separate from their visible sources. Perhaps most formidable of all, Mond encounters serious challenges when confronted with the cosmic microwave background, that ancient light-carrying encoded information about the universe's early structure. The delicate ripples in this primordial radiation match beautifully with predictions from dark matter models, encoding a precise cosmic recipe for the proportions of ordinary matter, and dark energy. Modified gravity theories, which fundamentally alter gravitational dynamics, find it much harder to reproduce these subtle imprints without introducing additional complications or inconsistencies. This mixed success inspired a broader family of theories collectively known as modified gravity, extending beyond Mond's specific proposals to explore various ways that gravitational physics might deviate from Einstein's general relativity on cosmic scales. Some frameworks, like Bekenstein's tensor vector scalar theory, introduce additional fields that subtly alter how gravity behaves across vast distances. Others propose that space-time itself possesses properties we haven't yet recognized. A few ambitious theories even attempt to explain both dark matter and dark energy as different manifestations of the same underlying modification to gravitational physics. These alternative theories can sometimes mimic dark matter's effects with surprising accuracy, providing elegant explanations for galaxy rotation curves while avoiding exotic particles. For many physicists, this theoretical economy represents a compelling virtue. If simple modifications to well-established laws can explain observations without requiring invisible matter, shouldn't we prefer such economical solutions? However, the more scientists test these modified gravity theories against the full range of astronomical observations, the more the evidence seems to favor the dark matter paradigm. When researchers simulate the universe's large-scale structure using only modified gravity, they struggle to reproduce the intricate patterns of the cosmic web, those filaments and voids stretching across billions of light-years. Dark matter models, by contrast, naturally generate structures matching telescope observations with remarkable fidelity, suggesting that invisible matter provides a more complete description of cosmic architecture. Even so, modified gravity theories serve crucial roles in the scientific process that extend far beyond their specific predictions. They act as essential counterweights to the prevailing dark matter paradigm, forcing researchers to constantly re-examine assumptions, sharpen models, and seek ever more stringent observational tests. The history of science overflows with moments when seemingly certain theories required fundamental revision, and modified gravity keeps this intellectual humility alive, providing a persistent voice asking, what if we've simply misunderstood how gravity works? Some researchers now explore hybrid approaches that combine elements of both perspectives, suggesting that gravity might indeed be slightly modified while invisible matter also exists in forms we haven't yet identified. The universe rarely offers either-or solutions to its deepest mysteries, often preferring both and scenarios that challenge human tendencies to oversimplify cosmic complexity. For now, the balance of evidence strongly supports dark matter's existence, with its gravitational fingerprints appearing consistently across every scale from dwarf galaxies to the largest observable structures. Yet modified gravity theories continue refining themselves, proposing new tests and predictions that might eventually reveal subtle deviations from standard physics. This ongoing dialogue between competing explanations represents science at its healthiest, a conversation where even theories that don't ultimately prevail contribute by forcing successful ones to prove themselves more rigorously whether the final answer emerges from exotic particles, modified physics, or some elegant combination of both. This theoretical tension has already enriched our understanding of cosmic architecture. Every alternative forces the standard model to sharpen its predictions. Every challenge reveals new questions worth investigating. And every debate reminds us that our current understanding, however impressive, remains wonderfully incomplete. As we step back from these competing explanations and survey the broader landscape they illuminate, we find ourselves naturally drawn to contemplate the universe's true composition, the precise recipe of visible and invisible ingredients that combines to create the cosmic architecture we observe stretching across 13 billion years of space and time. If dark matter truly dominates the cosmic census, then what exactly is the universe made of, and how do all its components fit together into the magnificent whole we call home? As we step back from these competing explanations and survey the broader landscape they illuminate, the patient underground experiments, the ambiguous cosmic whispers, the thunderous particle collisions, and the elegant theoretical alternatives, we find ourselves naturally drawn to contemplate perhaps the most profound realization to emerge from this century-long detective story. When astronomers carefully tally everything the universe contains, using multiple independent lines of evidence that converge with remarkable precision, something quietly astonishing comes into focus that fundamentally transforms our understanding of existence itself. Everything you can see, touch, or directly observe, every star painting light across the night sky, every planet orbiting in its cosmic dance, every nebula glowing with stellar fire, every atom composing your body, every molecule of air you breathe, together amounts to just about 5% of the cosmic total. 5%. The remaining 95% belongs to realms we cannot touch, taste, or illuminate with any instrument yet devised by human ingenuity, revealing themselves only through their gravitational influence on the tiny fraction of the universe we can actually observe. This cosmic census reads like an accounting ledger for existence itself, derived from the most precise measurements in the history of astronomy. The ancient light of the cosmic microwave background provides our most reliable cosmic recipe, its delicate temperature variations encoding the exact proportions of everything that exists. Roughly 27% consists of dark matter, those ghostly particles we've been pursuing through underground laboratories and cosmic observations, the invisible scaffolding that holds galaxies together and shapes the universe's largest structures. An even more mysterious 68% belongs to dark energy, a property of space itself that drives the universe's expansion to accelerate, stretching the fabric of space-time with gentle but relentless persistence. These numbers aren't rough estimates or educated guesses. They represent measurements encoded directly in the cosmos itself. written in the acoustic signatures that rang through the early universe when it was hot enough for sound waves to propagate through the primordial plasma. Missions like WMAP and Planck have traced these ancient echoes with such precision that we can determine the universe's composition to within fractions of a percent, creating the most accurate inventory of reality ever achieved. To truly grasp these proportions, imagine standing inside a vast cathedral so enormous that its walls vanish into darkness beyond perception. The few beams of light streaming through stained glass windows represent the stars, galaxies, and all luminous matter, that precious 5% that captures our attention and inspires our wonder. The invisible pillars supporting the ceiling, the unseen arches shaping the space, and the transparent air filling every corner, that's the dark matter and dark energy, the 95% that doesn't glow but makes the cathedral's existence possible. Without this hidden architecture, the entire structure would collapse, leaving no stage upon which light could perform its brief and brilliant dance. The ordinary matter that forms everything familiar represents a cosmic rarity, like scattered jewels in an ocean of the invisible. We are, in the most literal sense, beings constructed from stardust, not metaphorically, but with atomic precision. Every carbon atom in your body was forged in the nuclear furnace of a dying star. Every oxygen molecule you breathe was created through stellar nuclear synthesis and scattered through space by supernovae explosions. Yet even this remarkable atomic heritage constitutes only the tiniest fraction of what the universe actually contains. Dark matter's 27% provides the gravitational scaffolding that allows galaxies to form and persist across billions of years. Without its invisible embrace, stars would drift apart like scattered embers, and the elegant spiral arms we admire through telescopes would unravel into cosmic chaos. This patient architect operates with cool indifference to electromagnetic forces, shaping cosmic structure through gravity alone while remaining forever aloof from the light-based interactions that define our everyday experience. Our energy's dominant 68% represents perhaps the most mysterious component of all. Unlike matter that clumps and clusters, dark energy appears uniformly distributed throughout space, exerting a gentle outward pressure that ensures the universe continues expanding at an accelerating rate. It's as if space itself possesses an intrinsic tendency to grow, breathing the galaxies farther apart with each cosmic moment. This isn't empty void, but rather the most fundamental aspect of existence, the stage upon which all cosmic drama unfolds. What makes this inventory particularly remarkable is our cosmic timing. We exist at a unique moment in universal history when dark matter still binds galaxies and clusters together, but dark energy has begun to dominate the expansion. Because we inhabit this brief middle movement, we can still see far enough across space and time to map the cosmic web, measure ancient ripples, and determine the universe's recipe with precision. In the deep future, the very rulers and candles we use for these measurements will grow mute as distant structures recede beyond visibility. This dominance of the invisible doesn't render the universe cold or indifferent. Quite the opposite. It reveals a cosmos of extraordinary elegance and balance, where unseen forces collaborate to create conditions necessary for complexity, beauty, and consciousness to emerge. The spaces between galaxies, often described as empty voids, actually teem with dark energy's gentle influence and quantum fluctuations too subtle for direct detection. What we call nothing is actually the most fundamental something there is. Perhaps most remarkably, we represent extraordinary concentrations of the rare atomic matter that makes up less than 5% of existence. Yet from this cosmic minority arises awareness, the capacity to look outward, take measure and find pattern in the whole. We are the universe's way of examining its own invisible architecture, temporary arrangements of rare matter guided by unseen hands into forms capable of wonder, curiosity, and love. The fact that we can measure these cosmic proportions so precisely even without understanding what most of the universe actually is, represents one of the quiet triumphs of human curiosity. The unknown isn't an obstacle to knowledge, but rather its wellspring, constantly revealing new horizons that deepen rather than diminish the cosmos's mystery and beauty. Each discovery doesn't close the book on cosmic wonder, but opens new chapters filled with questions we hadn't known how to ask as we drift toward the conclusion of our gentle journey through the invisible universe. This cosmic inventory naturally points us toward contemplating what lies ahead. If dark matter and dark energy truly dominate existence, what does their patient influence mean for the ultimate fate of galaxies, stars, and all the luminous beauty that currently graces our night sky? The same forces that shape the universe's past continue writing its future, leading us toward a vision of cosmic destiny, both serene and profound, where darkness ultimately inherits everything while somehow making eternal space for light's brief and precious dance. From this cosmic inventory, where ordinary matter represents merely 5% of existence, while dark matter and dark energy dominate the universal stage, our gentle journey through the invisible naturally draws us toward one final contemplation. The same forces that shape the cosmos's past and govern its present continue writing its future with patient, inexorable certainty. If we follow their quiet influence forward through deep time, across scales that dwarf human comprehension, we discover that the story of the invisible is ultimately a story about eternity itself, where darkness doesn't represent an ending, but rather the universe's most enduring foundation. The night sky we admire today, with its glittering galaxies and shimmering nebulae, represents only a temporary arrangement in a much longer cosmic narrative. Stars burn through their nuclear fuel with brilliant intensity, but even the longest-lived red dwarfs will eventually exhaust their hydrogen and fade to cold, dark remnants. The luminous epoch we're privileged to witness, this brief age of fire and light, occupies merely the opening chapters of a story that will continue for trillions of years into a future dominated entirely by the invisible. Dark energy's gentle push ensures that the great tapestry of the cosmic web grows ever thinner with time. The delicate filaments stretching between galaxy clusters will elongate and snap, while vast voids expand like cosmic lungs slowly exhaling. Distant galaxies already speed away from us, and in the far future their recession will outpace any hope of communication. Each gravitationally bound cluster will become an island universe, surrounded by an ocean of darkness so vast that no light from neighboring regions can ever bridge the expanding gaps. Within these isolated cosmic archipelagos, stellar evolution continues its patient work. The massive blue giants that currently illuminate spiral arms with brilliant fire will burn out first, their intense luminosity ensuring brief but spectacular lives. Medium-sized stars like our Sun will swell into red giants before collapsing into white dwarfs, dense, hot remnants that slowly cool over trillions of years until they become invisible black dwarfs cold as the space around them. The smallest red dwarf stars will persist longest, their frugal nuclear burning allowing them to shine for tens of trillions of years, serving as the universe's final lighthouses in an ever-darkening sea. Throughout this gradual dimming of the cosmic lights, dark matter maintains its silent vigil. The invisible halos that currently cradle galaxies will persist long after their luminous contents have faded, continuing to define gravitational landscapes even when there's no longer any light to reveal their influence. These ghostly structures preserve the memory of cosmic architecture, maintaining the shapes and patterns established during the universe's youth like ancient stone foundations outlasting the buildings they once supported. In time, scales that challenge imagination, even black holes, those gravitational monsters that seem permanent and indestructible, will begin to evaporate through Hawking radiation. The largest supermassive black holes will take so long to disappear that the number of years required would fill libraries with zeros. Yet eventually even these final remnants of cosmic violence will fade away, releasing their captured mass back into the expanding void as the faintest possible whisper of photons. What remains after this ultimate dissolution is a universe filled primarily with dark matter particles, still drifting through space, but now spread so thin they might never encounter each other again. These ghostly remnants of the cosmic web will continue their eternal dance, too diffuse to collapse under their own gravity, too stable to decay into anything lighter. They represent the universe's most persistent memory, invisible. Matter that was present at creation and will endure until the final moment. There's something profoundly peaceful about this vision of the far future. The universe doesn't end in violence or chaos, but settles into a state where change becomes so gradual it might as well be stillness. The same dark matter that shaped galaxies during the cosmos's youth will be there at its end, patient and unchanging, like ancient pillars supporting an invisible cathedral long after its congregation has departed. To imagine standing inside such a vast cathedral helps us grasp this cosmic destiny. The few beams of light streaming through stained glass windows represent the stars and galaxies, that precious 5% that captures our attention today. But the invisible pillars supporting the ceiling, the unseen arches shaping the space, and the transparent air filling every corner, that's the dark matter and dark energy that will inherit everything. Without this hidden architecture, the entire structure would collapse, leaving no stage upon which light could ever perform its brief and brilliant dance. Perhaps most remarkably, this cosmic future belongs entirely to the dark. The visible matter that currently defines our experience represents merely a brief flowering in a much longer story written in invisible ink. We exist during the universe's luminous childhood, when nuclear fires still burn and electromagnetic radiation still paints the sky with color and pattern. But the true foundation, the dark matter scaffolding that made our existence possible, will outlast every star, every galaxy, and every photon, carrying forward the geometric memory of creation itself. From this perspective, darkness reveals itself not as the absence of light, but as the universe's most fundamental and enduring aspect. The invisible matter we've been pursuing through underground laboratories and space-based telescopes represents not a mystery to be solved and forgotten, but the eternal substrate upon which all temporary beauty rests. We are temporary arrangements of rare atomic matter, briefly illuminated by stellar fire, swimming through an ocean of the invisible that was here before us and will remain long after our last light fades. This realization transforms our relationship with cosmic darkness from fear to wonder, from ignorance to appreciation. The night sky we see today exists because invisible hands have been shaping it with patient gravity for nearly 14 billion years. The same dark matter that guides galactic rotation curves also guides our solar system's journey through space, creating the stable conditions that allowed life to emerge and consciousness to contemplate its own cosmic context. As we drift towards sleep beneath this same sky, carried by invisible currents through the Milky Way's dark halo, we can find comfort in knowing that we're part of something both vast and intimate, temporary and eternal. The darkness surrounding us isn't empty but full of gentle presence, not hostile but protective, not meaningless but pregnant with the patterns that connect every scale of existence from quantum to cosmic. The future belongs to the dark, but in that darkness lies the foundation that makes all light possible, patient, enduring and quietly beautiful in its eternal embrace of everything that was, is and ever shall be. Tonight, the stars still shine because something silent keeps the rhythm, and in that balance between brightness and shadow, we find our place in the vast, gentle darkness that holds all things in its patient, loving arm.